Hi everyone, welcome to PrepFusion. So now we are going to study PN junction under reverse bias. Okay, so this was our PN junction under equilibrium. In equilibrium, what was the condition? There was some built-in electric field. This built-in electric field was there, which was making sure that drift and diffusion are equal. Basically, let's just say here on P side, electrons are the minority charge carriers, and on N side, electrons are the majority charge carriers. So whatever the number of electrons were drifting from here to here, the same number of electrons were diffusing from here to here as well. So drift and diffusion were equal. So the total current was actually 0. So this was the condition under equilibrium. Now I am reverse biasing the PN junction. What is the meaning of reverse bias? The P would be connected with negative, N would be connected with positive. So P would be connected with negative, N would be connected with positive. So what I am doing? Now I am applying a negative bias across this PN junction. So this side goes to negative and this side goes to positive. So I am applying an external field towards this PN junction. So external field has been applied. Now where most of the fields will be applied? The most of the field will be applied here, right? Most of the field will be going inside the depletion region only. Why inside the depletion region? Because depletion region is having the maximum resistance. That means whatever the potential that you are applying, most of the potential will be dropped across the depletion region only. So whatever the external field that I am applying, that external field has gone to that depletion region. Now what do you see? The built-in electric field and the external electric field both are in the same direction. That means now the effective electric field has increased. This has become E built-in plus E external. And since this electric field has become stronger, so what do you think? What will happen with depletion region? The depletion region will become wider, because what is the formula of depletion region? Depletion width. Depletion width is nothing but under root 2 epsilon by q 1 upon Na plus 1 upon Nd. And here previously we used to write down V built in, but along with V built in, now V reverse bias is also coming into action. Basically the total bias has increased now. Previously at the junction only V built in potential was there, but now at the junction along with V built in, some V reverse bias potential is also coming. Here what is V reverse bias? V reverse bias is nothing but, let's just say this kind of resistance was Rs. The neutral side was having a resistance of Rs. Depletion region was having a resistance of R depletion. And again the neutral side was having a resistance of Rs. So whatever the potential that you are applying, I am applying the potential of VA. So whichever the part of VA is being dropped across R depletion, that is nothing but VR. Okay, and you would know that VR would be always approximately equals to VA only. Okay, so since the effective electric field has increased, now depletion width has also increased. So what will happen is that this was the condition under equilibrium. Now the depletion width will increase. Depletion width will increase. This depletion width will be increasing. Sir, where those holes go? Like someone would be saying that, sir, this particular scenario was having some holes. Here some electrons would be there. But in the depletion width, there cannot be any charge carriers. So these electrons and holes will be gone. These electrons would be gone. So these holes will be gone. These electrons will be gone. These electrons will also be gone. So how those electrons and holes got eradicated? So there was one hole there, but from the battery, electron was supplied. So this electron was recombining with the hole, right? From the battery, whatever the electron came out, that electron recombined with the hole. Actually, that electron first recombined with this hole, then this hole traveled here. Are you able to understand this point? Okay. So from the battery, whatever the part was there, like this hole was there, so battery is making sure that this hole gets recombined, and whatever the electron was there, this battery is making sure that this electron gets recombined. So we are disturbing the equilibrium. How we disturb the equilibrium? What we have done? There was some built-in electric field which was making sure that amount of drift and diffusion are equal to each other, so total current is 0. But now what we have done? We have applied a reverse bias. What that reverse bias is doing? That reverse bias is actually increasing the effective electric field. Because of that, what will happen? This barrier will increase now. Previously, this was your equilibrium condition. This was my equilibrium condition. But now what will happen? The barrier will increase. And from the other scenario as well, you can understand it. Here there are holes. On this side, there are holes. So negative multiply with positive. What does that mean? Negative. That means the energy of holes is decreasing. Energy of holes is decreasing. And for the holes, energy decreases in upward direction. So this particular part would go upward, right? Energy of holes are decreasing. Since we have applied negative here, negative multiply with positive, negative. That means energy of holes is decreasing. For the holes, if energy increases, they move upward. And what about the electrons? Positive multiply with negative, that means you are getting negative only. That means energy of electrons are decreasing. If the electron energy decreases, that means they move downward, because the energy of electron decreases in the downward direction and increases in the upward direction, and the energy of holes increases in the downward direction and decreases in the upward direction. So both electron and holes energy are decreasing. So holes will move upward and electrons will move downward. So what will happen is that this particular part, which part? This particular part will move upward and this particular part will move downward. Along with that, another thing is that this depletion width will also increase. Previously the width was lesser, like they were nearer, but now they will be farther away, right? Because depletion width is also increasing. So now what will happen? This kind of a slope we will be getting. And you can see that the barrier has increased. This barrier has increased. This barrier has become V built-in plus V reverse biased. Okay, same will be this barrier as well. You don't need to show it because you know that face of EC and face of E will be same, right? If you want to join them, you can join them as well. But let's not do anything with the EFP and EFN, okay? Because you know that with respect to Fermi level, we don't do anything, right? So this is with respect to energy band diagram. With respect to energy band diagram as well, you can explain anything. What you can explain? Sir, here there are majority electrons, here there are minority electrons. Sir, previously when this barrier was there, they were not able to diffuse, right? When this barrier was there, sir, they have to go to this much of height. That means diffusion was very less. Now the height has increased. So diffusion has become much more lesser. But if I give them some force, what will happen? They will roll down very fastly. That means drift has increased now and diffusion has decreased. I hope you are able to understand. Like at least 10 times I have explained this particular thing with the different scenarios. So now you will be able to understand what is happening here. Sir, in this scenario as well, we were not able to diffuse much, or whatever the amount of diffusion was there, the same amount of drift was also there. If I put the force, whatever the force that they are getting, the same amount of diffusion was also there. Electrons were going from here to here, electrons were coming down as well. That means drift and diffusion were equal. But now since I have increased the barrier, so if you are standing here, now what you will feel? Sir, it will be tougher to go upward because the barrier has increased. But if I give you some force, whatever the amount of force I was giving you here, if I give you the same amount of force, you will be rolling more, right? You will be rolling more. What does that mean? That simply means that the drift has increased and diffusion has decreased. So what do you understand? And same scenario you can explain by the holes as well. Here there would be majority number of holes and here there would be minority holes. So holes likes to move upward because of that drift, and they want to go here to here because of the diffusion. But since this barrier is larger, since this barrier is larger, now they will not be able to, here Q I should write down, right? Because this is energy. So since this barrier is larger, they will not be able to diffuse much, but they will be able to drift in a good manner, right? So drift has increased and diffusion has decreased. Physically, if you want to understand, like physically what is happening, so you see here. So here the electric field has become stronger, right? Electric field has become stronger. Now in the depletion region, there will be some electrons, like here on this side, there will be some electron and holes. Some electron and holes would be there. And here as well, some electron and holes would be there. Let's make the same number. Here as well, there would be some electron and holes. Although on this side, there will be more number of electron and lesser holes. And here there would be more holes. Now what this electric field will do? This electric field will put force on the opposite direction to the electrons. That means now these electrons, whatever the electron was that was present here, because of this electric field, this electron would be moving here. So this is your electron drift. And here whatever the holes were there, these holes will be drifting here. This is your hole drift. And because of that, there would be a current in this direction, right? Because if, sorry, there would be a current in opposite direction. So this would be your drift current. Say yes or no. Right? Electrons are drifting here, holes are, because of this external electric field, external plus built-in. Because of this built-in and external electric field, the electrons are drifting in this direction and holes are drifting in this direction. Because of that, the current is flowing, and the current would flow from here to here. That this would be the direction of current. This is how the current is flowing. Okay, so current is flowing in this manner. So this will be the direction of current. But this current is coming because of minority carriers only, because in the depletion region there are very less carriers. So the current amount would be very less. Let me explain it again. What I am saying, the current is coming because of the minority carriers only. No, because whatever the electron and holes are present in the depletion region, those electron and holes are moving. These electron and holes are not moving. Whatever the electron and holes are present in the depletion region, those electron and holes are moving, and those electron and holes are minority. They are very less. I should not say minority, I should just say that in the depletion region, very less number of electron and holes are present. And since very less number of electron and holes are present, that means there will be very less amount of current. So in the forward bias, I was getting a current exponential, and in the reverse bias, I am getting very less current. So do you remember what was my target? That as I change the polarity of the battery, my current should be controlled. So when I was having, let's just say this VA is 5 volts. So when I applied VA equals to 5 volt, I was getting good amount of current. But when I am applying VA equals to minus 5 volt, I am getting nearly zero current or very less current. And this is what I wanted. Just as I change my polarity, my current should be changing. So at 5 volt, I am getting very good amount of current, and at minus 5 volt, I am getting very less current. And this is what I wanted, and that I have achieved with PN junction forward bias and reverse bias. Is that clear to you? Okay, well and good. So this is the scenario here, right? Now another question can be asked that, sir, you said that from here electrons will be moving, right? Electron would get some force because of this electric field. Electrons would get some force and they will be moving. This is what you said. Why these electrons cannot move? What I am saying is that on n side, if you remember the concentration plot, if you remember our concentration, let's make it on the next page only. If you remember the concentration plot, this was the concentration plot, no? Under equilibrium, I am saying. Under equilibrium, I am saying this was your concentration plot. So this line was for holes. Which line? Let's make it a different color of pen only. So this line was for holes and the green line was for electrons. And this line was for electrons. So in the depletion region, here holes are present, here electrons are also present. So let's just say here 2 electrons are present. So on this side 4 electrons will be present, no? What I am saying is that between 0 to xn, 4 electrons are present. Between 0 to minus xp, 2 electrons are only present. But you are saying that these 2 electrons will be moving. You do not even care about these electrons. Are you able to understand the doubt what I am saying? I am saying that, sir, you are caring about these 2 electrons. You are saying that minority carriers of p side will be moving. But why you are not saying that, sir, these will also move? Can you think of it? Whenever you have applied this external field, who will feel more force? This electron will feel more force or this electron will feel more force? The field has been applied in this manner, right? The positive part goes here, the negative part goes here. So if I say there is 1 electron present here, that means that 1 electron will get only this much of potential. But if there is this electron that is present here, this electron will get more potential. That means this particular electron which is present on p side, that will get more force than this electron which is present on n side. Although this electron will also move, but the energy of this electron will be much higher, because electron just doesn't need to move. What electron needs to do? electron will move and it will move such that it should reach to the positive terminal of battery. So if electron is able to complete the path, then only the current would flow. Let's just say electron got some force and it has moved till this point only, then current will not flow. The electron has to move and completely it has to move till the positive terminal of battery. So who is getting more force? Which electron is getting more force? The electron which is present on the p side, that is getting more force, no? Just a very deep point. Okay, I don't think anyone would be asking it, but someone who is studying, he can get it out that, sir, why these electrons are moving, why these electrons are not moving, why minority electron concentration on the p side is moving, why the majority electron concentration on n side is not moving? Because, sir, this was the graph under equilibrium. So here there are 4 electrons and, sir, here there are only 2 electrons only, because electron concentration is increasing. The same scenario you can understand with the holes as well, right? So, sir, why it is happening? So the reason is clear to you, right? You can understand from here as well. 1 electron will be present here. Which electron I am talking about? I am talking about these 2 electrons. So these 2 electrons will be present here and these 4 electrons will be present here. If you are standing here and if I give you some force, and if you are standing here, then I give you some force, where you will feel more force? On both of the side I am applying a force of 1 Newton only. I am pushing you with the same force. But if you are standing here, you will be rolling with more force, right? Now someone would say that, sir, if I am standing here I will feel the maximum force. Sir, if I am standing here, let's just say, sir, here also there will be some minority electrons present, no? So these electrons should feel the maximum force. But what is actually happening? Whatever the external field that we are applying, that is reaching in this region only. So here these electrons are feeling very, very lesser force. These electrons are not feeling much force. So who is feeling the maximum force? The maximum force is felt by someone who is standing here or someone who is standing here. So they will be getting the maximum force. So that's why they will be contributing in the current. Same goes for holes as well. So whoever are standing here, like whatever the process that happens with electrons, the opposite process happens with holes, that you know, right? So those holes which are standing here, they will feel the maximum force. So they will contribute in the current. So what all are these holes? These holes are the minority carrier concentration on the n side. So that's why you would see the statement written that in reverse bias, the current is controlled by minority carrier concentration. By minority carrier concentration, what a lot of students think? They think that, sir, whatever the electron and holes are present in the depletion region, they are contributing in the current. No. All the electron and holes in the depletion region, they are not contributing in the current. The electrons which are present on the p side and the holes which are present on the n side, they are contributing in the current. Are you able to understand this statement or not? This will not be written in the theory, okay? Not very useful, but still, are you able to understand this point? The electrons which are present here and the holes which are present here, they are contributing in the current. Or who can contribute? The electrons and holes which are present near to the depletion region. Because near to the depletion region as well, there will be high amount of force, no? Let's just say there is some electron present here. There is some holes that are present here. So they will also feel high amount of force, holes. So they will also feel high amount of force. So they can also contribute in the current. Are you able to understand this point? But whatever the electrons that are present here, they are not contributing in the current. Whatever the holes that are present here, they are not contributing in the current. That means majority carrier concentration is not contributing in the current. My question will state away would be that why in the reverse bias, the majority carrier concentration doesn't contribute in the current. So that question would come up and people will be explaining this scenario, but they would forget the fact that this particular scenario, that, sir, this particular electron is getting much more force than these 4 electrons. Although they are majority here, although they are having high amount of number, but still, sir, they are getting more force, so they will contribute more. So these higher number will not be contributing in the current, but these lower number will be contributing in the current. And opposite goes for holes as well. That these lower number of holes will be contributing in the current, but these higher number of holes will not be contributing in the current. Is that point clear to you or not? So reverse bias theory is clear. I hope it is completely clear. Again, let's repeat. This was the barrier. In the examination or in some interview, if someone asks you that explain the reverse bias mechanism, then this is how you will be explaining. That, sir, built-in potential was there. I applied external battery in a manner that it is supporting the built-in electric field. So because of that, the barrier got increased. That means the diffusion has become tougher now, but the drift has become easier. So it would be, the current will be drift dominating. Now the drift current component would be 2 kind of component. whatever the electron and holes are present, they will be contributing in drift. But electrons from here will be contributing and holes from here will be contributing. Why electrons from p side will be contributing? Because electrons at the p side is getting more force because of the applied field. So they will be contributing more than these electrons. So that's why we say that minority carrier concentration of p side, which are electrons, and minority carrier concentration of n side, which are holes, will be contributing in the reverse current. What is reverse current? What is reverse current? Reverse current is the current that is flowing in the reverse bias. There were two terms, reverse saturation current, and there is a current called reverse current. What is reverse saturation current? That is I naught, that we have already seen. And what is reverse current? Reverse current is the current that is flowing in the reverse bias. What is forward current? Forward current is the current that is flowing in the forward bias. So if I say reverse saturation current depends on the minority carrier concentration, no. Reverse current depends on the minority carrier concentration. Okay, this is very confusing a lot of time. Like people get confused with the term reverse saturation current. So reverse saturation current is a different parameter. Reverse current is a different parameter. Reverse current is the current that is flowing in the reverse bias. So that reverse current would depend on the minority carrier concentration of p side and minority carrier concentration of n side. Is that clear to you? Okay. All good? All fine? Okay then. So this is the theory that has been written. Now you will not be able to understand this particular theory, but we will talk about it later on. As of now, let's read first and second paragraph. PN junction is reversed bias, P is connected to negative, N is connected to positive. The applied voltage increases the barrier potential across the junction. As a result, the depletion region will become wider and the electric field inside the junction would become stronger. Why it is becoming stronger? Because E built in plus E external. The majority charge carriers that are holes in the p side and electrons in the n side are pulled away from the junction. Because of this, almost no majority carriers are able to cross the junctions, right? Basically, majority carrier concentration are not able to contribute in the current. Minority carrier concentration are contributing in the current, right? So only a very small number of minority carrier concentration electrons in the p side and holes in the n side are able to move across the junction, and they form a very small amount of current called reverse current. This is your reverse current. This current is almost constant and very small in magnitude. We will talk about it. Why it is almost constant and very small in magnitude. We will talk about it. Okay, don't worry about it. Now, now it feels like that, sir, in reverse bias the current will be very less, right? It feels like that, sir, in reverse bias the current would be very less. But as you keep on increasing reverse bias, there will be some mechanism would be happening, and because of that mechanism, the current will rise instantaneously, like very high current would flow. It feels like that, sir, if I am increasing this VA voltage, then the current would not change much. The current is already very low. But if you keep on increasing this VA voltage, something would happen. What would happen? We will surely discuss in this video only. Something would happen that would make the current rise very fastly. Like very huge amount of current would flow, and that condition is known as breakdown. So this has been written here. Okay, this theory has been written. If the reverse bias voltage is increased beyond a certain limit, a condition called breakdown occurs due to strong electric field inside the junction, and the current will rise up sharply. Thus, under the reverse bias, the diode doesn't conduct the current except for a very small current until breakdown takes place. So when that breakdown would be taking place, a very huge amount of current would be flowing. So basically, till some point, the very small current, and suddenly very large current will flow. So this kind of characteristics we get. Surely we will discuss it. But as of now, what you need to see, so there is reverse bias. Since there is reverse bias, so this electric field is becoming stronger. Diffusion has become very lesser. Only minority carrier concentration from the p side and minority carrier concentration from the n side are contributing in the current. And since they are very lesser, the current would also be very, very less. That's it. This is what you need to understand as of now. When you keep on increasing this reverse bias, something would happen, some scenario would take place that is known as breakdown, and because of that particular breakdown, the current will rise instantaneously. Sir, why that happens? What is the logic behind that? What is the reasoning behind that? Everything we will discuss, but when the right time comes. Okay, at that time we will discuss it. Now you would see that in GATE PYQs, a lot of questions are framed from reverse bias. Sir, ideally you should be teaching current equation now, right? In forward bias, what was our scenario? That first we understood the physical meaning, then we understood by the energy band diagram, then we saw the theory, and then we moved towards the current equation. Although we build up the concept of current equation, we saw the carrier concentration plot and then we saw current equations and all. But suddenly, sir, here you are coming to the formula of depletion width. Why is that so? It is not that important for understanding, but in the examination, there has been a lot of questions from the depletion width of reverse bias. So for your examination purpose, it becomes important. That's why we will simply see this formula that you already know. And based on this formula, we will solve a lot of numerical. 3 numericals we are going to solve. There a lot of questions would be there. In one numerical only, you would find 3 to 4 questions are there. So that's why we are not putting much focus as of now on the carrier concentration plot or on the current equation. We are putting our focus on the depletion width. In the forward bias, we did not discuss depletion width, hardly for 5 minutes we discussed about the depletion width. But in the reverse bias, it becomes very important. Why it becomes very important? That question paper setter knows. Because if they want to frame a theory, if they want to frame a numerical problem, no? Like if they want to give data, then this is the best possible, topic from where they can frame the problems. So if you see the previous year questions of PN junction, I would say 60% of the problems would be coming only from the depletion width of reverse bias. 60%. Are you able to understand this point? Like in 60% of the questions, you would have to apply this particular formula, which you already know. So for the equilibrium condition, this is your equilibrium condition. So in the equilibrium condition, what was your formula for depletion width? This is your equilibrium and this is your reverse bias. So what was the formula of depletion width? So 2 epsilon by q 1 upon Na plus 1 upon Nd V built in, right? This was the formula. Now what will be the formula? So depletion width has increased. Why it has increased? Because of this applied bias. From this applied bias, most of the potential will be reaching here only. So here, all the time, always you will take VA equals to VR. In the examination, they would mention the reverse bias of 10 volt is applied. Now you would not be thinking that, sir, out of 10 volt, how much will be dropped across the depletion? Whole 10 volt will be dropped across the depletion. By default, you need to take this consideration. Okay. So what will be your depletion width now? The same formula, in place of V built in, what you will write down? V built in plus VR. So from here, if you take V built in common, what you will get? Can you take V built in common? So can I write it down directly, or let me explain in the rough? 2 epsilon by q 1 upon Na plus 1 upon Nd. I have taken V built in common, right? So what I am getting? 1 plus VR by V built in. Say yes or no? V built in I have taken common. Now this much part, what do I know? This much part is W naught. Depletion width under equilibrium. Multiply with multiply with 1 plus VR by V built in, right? Just took a V built in common, so this became W naught multiply with under root 1 plus VR by V built in. So this is my depletion width under forward bias, under reverse bias, which has been increased. Okay, so better remember this formula only, or you remember this formula, from this formula as well, you will be able to write down this particular formula. Along with that, what you can see here, V built in is a constant value, no? Like basically, can I write down this W as W naught V built in plus VR, or forget about it. Let's see from here. This much part is a constant value. Constant or uniform, whatever I want to say. Epsilon will not change, Q will not change. This will depend on doping. So directly I can see that, sir, my depletion width will depend on V built in plus VR. Say yes or no? Depletion width will be proportional to V built in plus VR under root. So depletion width is proportional to this. Also you need to remember. If VR is 0, that means there is no reverse bias. What does that mean? That means depletion width is simply proportional to under root of V built in. If reverse bias is there, that means depletion width will be proportional to under root V built in plus VR. Okay. What about the maximum electric field? Here, what was your maximum electric field? Sir, Q and D xn divided by epsilon or Q and A xp divided by epsilon. So this was your E naught max. Here, what will be my E max? Same formula would be there, sir. No change. But here it would be xn naught, here it would be xp naught. Xn naught, xp naught. But here it would become Q and D xn upon epsilon, Q and A xp upon epsilon. Sir, why this formula has taken place? Because xn and xp has changed now. So this xn and xp would be coming from this W, right? The formula remains the same. Total charge divided by epsilon. Total charge per unit area divided by epsilon. Total charge per unit area divided by epsilon. Total charge per unit area divided by epsilon. Here also the same thing is there. It's just that xn naught, xp naught, xn naught has become xn, xp naught has become xp. So all the formula that you already know, simple, same formula are there. Just slight modification is there. The depletion width has changed. What depletion width has done? Depletion width has done this particular thing, that now previously depletion width was proportional to V built in only, but now it has become proportional to V built in plus reverse bias. There you go. Okay. So we will solve some numericals. You can solve this particular numerical. You can try doing it on your own. Then you can try doing this one on your own. And then you can try doing this one on your own. Okay. 3 numericals we will solve. Out of 3, I guess you will be able to solve 2. Okay. This you would be able to solve, I guess. And out of these 2 as well, you can try solving one of them. So I will take a break because something is happening in my throat. So I will take a break and then I will come back. Okay. Yeah, welcome back. So did you try this question? What is given? PN junction with the doping of Na and Nd is given. The ratio of Na ratio Nd is given. Na ratio Nd, that is 1:2. Okay. So from here, can you let me know what will be the ratio of Xn ratio, Xp ratio Xn? So that would be opposite, right? Na ratio Nd, Nd is having 2 ratio. That means doping on the N side is more. That means the depletion width on the N side will be lesser. That means it would be 2:1, right? Now what is given? Depletion width on N side under equilibrium is given. That means the value of Xn naught is given, that is 4 micrometer. So can you let me know what will be the value of Xp naught? Surely, sir, it will be doubled. That would be 8 micrometer. That means what was the depletion width under equilibrium? Sir, that was 12 micrometer. What they want you to ask? When a reverse bias of 1.7 volt is applied, what will be the new depletion width? This is something that they are asking. So what I need to find out? I need to find out the depletion width, and I know that depletion width is proportional to V built in plus VR. What really happens is that a lot of time people forget this V built in. So never ever forget this V built in, otherwise everything would be matched up. Okay. Answer would be completely different. So don't forget this V built in. So I need to find out depletion width when there is a forward bias of 1.7 volt. So that would be proportional to what? That would be proportional to V built in, which is 0.3 plus 1.7. What I can take, since there is a proportionality sign, so I can take the ratio. Depletion width under equilibrium, what that was proportional to? Sir, that was proportional to simply 0.3 only. Is that clear to you? Like depletion width is simply some constant V built in plus VR. So depletion width under reverse bias of 1.7. So that would be 1.7 plus 0.3, that would be under root 2. Then depletion width under equilibrium. Reverse bias of 0, that means only built-in potential would come into action. When I divide both of them, what I am getting? W by W naught under root 2 divided by 0.3. This is something that I am getting. All good? So W would be under root 2 upon 0.3 into 12 micrometer. That would be the answer. And surely it will be greater than 12 micrometer only. So very easily I could have said 0.3 plus 1.7. That would be 2 divided by 0.3. Directly in the examination, I would have done this step. Right? Very simple question, very straightforward. And you would see that in PYQs, a lot of questions are asked from this particular pattern. Okay. So 3.98 micrometer you are getting. Although very straightforward, but a lot of questions are asked on this pattern only. So simply you see the width, what will be the ratio, then total depletion width under equilibrium we have find out, then you know that it will be proportional to built-in plus reverse bias. Let's go to the next one. This is a gate PIQ only. This was asked in gate examination only. Okay. So PN junction is given, doping profile is given. The length of N side is 0.2 micrometer. The length of P side is 1.2 micrometer. Na-Nd ratio is like Na-Nd doping is also given. V built-in potential is also already given. Q epsilon, all these values are mentioned. What you need to find out? You need to find out the magnitude of reverse bias such that it will completely deplete one of the two regions prior to the other. What does that mean? That means under the equilibrium, we were having some depletion width. Some depletion width we were having. So just let me know one thing. Here doping is more. Nd doping is more. That means Nd is more than Na here, right? Nd is more than Na. What does that mean? That means your Xn would be lesser than Xp. Even at the equilibrium or without the equilibrium as well. So basically depletion width on the N side would be lesser than the depletion width on the P side. But what would be their ratio? Can you let me know? Like if I say depletion width on N side is Xn, then what will be the depletion width on P side in terms of Xn? What I mean to say is that, sir, here I can see that my Na ratio Nd is nothing but 1:2. That means my Xp ratio Xn would nothing be but 2:1. That means my Xp would simply be 2Xn. Is that understandable to you? Depletion width on P side will simply be double of depletion width on N side because doping is also double, no? Doping on N side is double of doping on P side. So depletion width on P side would be double of depletion width on N side. Very simple thing. Now our matter of concern is which side will be depleted first. First N side will be depleted or P side will be depleted. That I need to think. So if I say that N side is completely depleted. So if I say if Xn is 0.2 micrometer, then what would be your Xp? Xp would be 0.4 micrometer. That means if I say that depletion width on N side has become complete region, that means depletion width on N side has become 0.2 micrometer, then the depletion width on P side would become 0.6 micrometer only. That means who got depleted first? N side got depleted first, no? Are you able to answer this point? Let's just say I thought that P side is getting depleted. P side is completely getting depleted. That means my depletion width on P side should have been 1.2 micrometer. That means my depletion width on N side would be half of that because Xn is equals to Xp by 2. So that would be 0.6 micrometer. But what you can see here, you are having the length of only 0.2 micrometer only. That means first N side will be completely depleted. Since N side is completely depleted, so what is the depletion width on P side? That would be double of that. That means depletion width on P side would be 0.4 micrometer. What does that mean? That means N side will be depleted. N side will be depleted prior to P side. Right? So what will be your depletion width under reverse bias? Depletion width under reverse bias, that would become 0.4 plus 0.2, 0.6 micrometer. So you need to find out the depletion width under reverse bias such that it has become 0.6 micrometer. What is the formula? 0.6 micrometer should be equals to under root 2 epsilon by Q 1 upon Na plus 1 upon Nd multiply with V built in plus Vr. You are having all the values. Na value I have, Nd value I have, epsilon value I have, Q value I have, V built in value I have. I need to find out Vr, and this value is also there. So only mathematics is left now. Another thing, everything is going in centimeter, centimeter, centimeter. So what I would do, 0.6 into 10 to the power minus 4 centimeter, right? Because it is micrometer, I need to convert it into centimeter. Everything is going into centimeter, and here I can do the square as well. 2 epsilon value they have mentioned, 12 I need to take. So 12 into 8.85 into 10 to the power minus 14 divided by Q, which is 1.6 into 10 to the power minus 19. 1 upon Na. What is the value of Na? 1 by 5 into 10 power 16 and 1 by 10 here, right? So 1 by 5 into 10 to the power 16 plus 1 by 10 into 10 to the power 16. V built in, what is the value of V built in? V built in is 0.8 and reverse bias I need to find out. So this calculation you need to do and do it on your own. Okay, I will simply write down the answer which I need to check because I also don't remember it. Or shall I do it on my own? 10 to the power 16 can get cancelled out from here. 1 by 5, 1 by 10, it would become 0 0.2, 0 0.3, 0 0.3. So we can do it. Let's try doing it. 0 0.6 square divided by 2 divided by 12. 2 divided by 12 divided by 8.85 and divided by 0.3 as well, right? By 0.3. All that is divided and then multiply with 1.6. Yeah, so roughly around 8.2 we are getting. Okay, reverse bias roughly around 8.2 volt we are getting. So this is the answer. Okay, the calculation will take some time. You can do it on your own. Answer would be 8.2 volt. Very simple only, right? It was very straightforward. You don't need to find out the depletion width under zero bias. Like you don't need to find out depletion width under equilibrium. That is not a matter of concern. Our matter of concern is under the reverse bias, what is the depletion width? And if you need to find out the depletion width under equilibrium, then what you need to do? Simply here you put 0 and all the values you are having, you will be able to find out the depletion width under equilibrium as well. But they are actually asking, you already know the depletion width under reverse bias, you just need to find out the value of reverse bias that would make you achieve this kind of scenario. Let's go to next question. This is a good question, I would say. Okay. What you need to find out in a reverse bias PN junction, the maximum electric field is given. For maximum electric field, I ask you to remember only one formula. It is under the reverse bias, right? But whether it is reverse bias or forward bias, I don't care. I only know that, sir, total charge per unit area divided by epsilon, or total negative charge per unit area divided by epsilon. So this formula I remember. Now Q and D epsilon, they will be constant only, but Xn and Xp would be changing with respect to the reverse bias. So now what the question is saying, Emax is given, Na and D are given, magnitude of reverse bias is Vr. You need to find out the magnitude of reverse bias. This is what they are asking. Okay. So from this formula, what I can get the value of Xn and Xp as well. Are you able to understand this point? So if I get the value of Xn and Xp, what I can do? Then I can do something about it, right? Because I would know the value of depletion width. Yeah. So now this question is making sense. Like from the given value, I can get the value of Xn and Xp. If I get the value of Xn and Xp, that means I can get the depletion width. If I get the depletion width, then what do I know? What is my target to find out? Reverse bias. So I know the formula of depletion width, no? What is that formula? The formula is very simple. So that formula is nothing but 2 epsilon by Q 1 upon Na plus 1 upon Nd V built in plus Vr. So this is the formula. So if I have the value of depletion width 2 epsilon by Q, Na, Nd, everything I am having, V built in I can find out. How will I find out V built in? So it is very simple. Kt ln Na Nd by Ni square. Okay. So I will get the value of V built in, from there I can get the value of Vr. So whatever that you know, just write down. Based on that, you will be able to solve the problem, that's for sure. Now let's just say in the examination, this Ni value was not mentioned. What I am saying, in the examination, this Ni value was not mentioned. So if Ni value is not mentioned, you will not be able to find out the built-in potential, no? Right? Built-in potential you will not be able to find out. So in the examination, somehow you are not able to find out built-in potential, then assume built-in potential to be 0. What I am saying, somehow in the examination, if you are not able to find out the built-in potential, then it means that built-in potential is much lesser than the reverse bias that you are actually applying. Although you don't know the answer, but you can see that answer is coming out to be 72.7 volt, which will be much greater than V built in. Are you able to understand this point? So answer would be actually much greater than V built in. So you can ignore V built in the examination if you feel like that, sir, I am not able to find out the value of V built in. But although in this question you will be able to find out the value of V built in because all the values are mentioned. So everything is mentioned. All you need to do is that apply the equation and get the answer. So apply the equation smartly. Emax. Let's try being more smart here. Like you can apply the equation, you can get the value of x and xp and you will get the answer. But let's try being more smart. What I can see here, you see the ratio of Na and D. Na ratio and D. What you can see? If I take the Na ratio and D, you can see that Na is 100 times of ND. That means it is your P plus plus N junction. Say yes or no? Are you able to understand this point? Na is 100 times of ND. What does that mean? That means your XP ratio Xn will be 1 ratio 100. What does that mean? Let's just say if Xn is coming out to be 100 micrometer, then XP would come out to be 1 micrometer, which is nearly nothing. 1 micrometer is nearly nothing to 100 micrometer. What does that mean? That means, sir, my W depletion would be nearly equals to Xn only. Are you able to understand this point? Are you able to understand this point? Because of this very high doping, this is something that I can conclude. That, sir, my W depletion is nearly coming out to be Xn only. That means this W depletion that I have written down, I can nearly put it as Xn only. Is that understandable to you? Now, what kind of formula I will apply? Let's apply the formula. Just doing some approximation, like all these approximations are fine as well. Why they are fine? Because, sir, 1 ratio 100. That means ND on the N side, there is very less doping. That means depletion width would be very, very larger on the N side. So, total depletion width would be nearly equals to Xn only, because total depletion width is Xn plus XP. Now this part would be nearly 0 compared to Xn. So Xn would be much larger than XP. That means your total depletion width would be nearly equals to Xn. Right? Now here depletion width has been replaced with Xn. Now what you can do on this side? 2 epsilon by Q. Now you know that Na is much larger than Nd. What you can see here, Na is much larger than Nd. That means 1 by Na will be much lesser than 1 by Nd. So this value 1 by Nd would be much larger than 1 by Na. That means you can ignore this one. So I am just telling in the examination what may happen. In the examination, what they can directly mention that it is your P plus plus N junction, and they don't even mention the value of Na. So if P plus plus N junction is there, that means Na is very much larger than Nd. That means 1 by Na could be ignored. So in this formula, you can ignore 1 by Na as well. Are you able to understand this point? And this kind of questions have been asked in the examination as well. What they did, they mentioned the data in a manner that you are not able to find out the value of, like they will not even give you the value of Na. That means you will not be able to find out the built-in potential. If you are not able to find out the built-in potential, then here what built-in potential you will apply? So you will have to consider that 0. Okay. And then they have not mentioned the value of Na. That means here also you will not be able to put any data. But what they have mentioned, it is P plus plus N junction. So if it is P plus plus N junction, that means Na value is very large. That means 1 by Na would be very much lower. So I can ignore that, and eventually I am getting 1 by Nd. And you could see that in the final answer, sir, you can ignore V built in as well. But as of now, let's not ignore it. So this much reduction we have done. Is that clear to you? This much reduction we have done in this formula. So from Emax, what was our Emax? Like I don't want to put the values as of now. I will put the values in the end. Qnd by epsilon. In place of Xn, I will put this formula. I cannot apply this formula, right? Because I don't even know the value of XP. What I have done, I have assumed XP is nearly 0. So I cannot apply this formula. Now, no one will say that, sir, XP is nearly 0. So this value will be 0 only. No. Na is very large. No. Very large multiply with very low. Some sufficient amount of value you will be getting. Right? You know that Nd into Xn is equals to Na into XP. Using all these expression only, we are getting till this conclusion. So Qnd by epsilon, and the formula of XP I can put, which is coming out to be 2 epsilon by Qnd, right? 2 epsilon by Qnd into V built in plus Vr. From here I can see that, sir, Emax is nothing but under root 2 Qnd upon epsilon, because under root Qnd, under root Qnd would be left, under root 2 will be left, and downward under root epsilon will get cancelled out, only under root epsilon will be left, right? V built in plus Vr. So from here I am interested in V built in plus VR only. So answer is coming out to be epsilon E max square, epsilon E max square, because this square goes here and epsilon goes, this square goes here, it will become E square, E max square into epsilon divided by 2Q and D. So this will be the formula we will be getting in Zener diode. Okay, this will be the formula of breakdown voltage of Zener diode. But you are not supposed to remember this formula. You will be able to derive in this manner. Okay, very simple derivation it is. Like, it is not even derivation, it is simply mathematics that you are doing. Now E max value I have, epsilon value I have, 2Q and D value I have. I care about the built-in potential that I can find out from here. So let's find out the built-in potential, which is not a big which is not a big matter of concern for me, because I know that it will come out to be nearly very lesser than VR. Na and D, what is the value of Na and D? 16 10 to the power 32, right? 16 10 to the power 32 divided by Ni square. Ni square will be 10 to the power 20. So what you are getting? 10 to the power 12 into 16, 10 to the power 12. Na and D, I have done the calculation correctly only, no? Yeah, 10 to the power 12 into 16, whatever it is, then you take a logarithm and then 0.0259. So it is coming out to be 0.78 volt. Okay, so V built in is coming out to be 0.78 volt. Now I need to find out 0.78 volt plus VR, what that would be equivalent to. What is the value of epsilon? Epsilon is 11.7 into 8.85 into 10 power minus 14. 11.7 into 8.85 into 10 to the power minus 14 into E naught square, right? So what is your E naught? E naught is everything in centimeter we will mention. So 3 into 10 to the power 5. So that would become 9 into 10 to the power 10, right? Square of this. So 9, 3 square 9, 10 to the power 5, that would be 10 to the power 10 divided by 2Q and D. 2 into 1.6 into 10 to the power minus 19 into ND. What is the value of ND? ND is 4 into 10 to the power 15. Okay, so this will be 10 to the power 5, 10 to the power minus, this would be 10 to the power minus 4. So basically this and this, everything is getting cancelled. So on the upper side 10 to the power minus 4, downward side 10 to the power minus 4. So everything is getting cancelled. Now what you can see, 11.7 into 8.85 into 9 divided by 2 divided by 1.6 divided by 4. So 72.8 you are getting. 72.8. So there the guy who wrote down the answer, he actually ignored the built-in potential. Okay, but different answer we are getting here. If you solve this one, this particular part is giving 72.8. So what will be your VR? VR will be nearly 72 volt. Okay. So in the examination in numerical answer type, it might be some issue, right? Because if someone write down 72.8, who knows, they have given the limit from let's just say 71.9 to 72.5, and someone would have written 72.7. So let's go by the exact analysis only in the examination. But these kind of question will not come in numerical type. This will come in MCQ. Like if very large value is coming, no, so they would set up the option in this manner. Like one option will be 72, one option will be 63, one option would be 57. So you would know that very large difference is there. Okay, so this question is also done, right? So good enough problem solving we have done. More questions we will solve, but as of now you have understood that what kind of questions can be asked in PN junction from reverse bias. So from reverse bias, they are very famous question actually. That's why we solved 3 questions here. Now we are going to study about carrier carrier concentration plot. Okay, which is very straightforward. You already know all the formula. So one thing I am going to tell now, whatever the formula that you have understood in forward bias, the same formula are there in reverse bias as well. You don't need to derive it. In forward bias, what did you write down? Like this was the equilibrium condition, and you know that, sir, under biasing, this is something I will get. n into p equals to ni square under equilibrium. Under biasing, this is the scenario. But here in reverse bias, only difference is this will be negative. That's it. Are you able to understand this point? This will just be negative. In forward bias, what did you write down? Sir, concentration of holes on n side at x equals to xn. Here, what was the concentration of holes? So that was Pn naught e to the power Va by Vt. Same formula will be applied here as well, no doubt about it. But Va would be negative, no? Let's just say Va is minus 1 volt. So your answer would be, sir, Pn naught, let's just say Pn naught was 10 to the power 4. E to the power Va is minus 1 divided by Vt. You see what is the answer you are getting? It is nearly 0. 1 divided by 0.026, then plus minus e to the power this much, and you see that answer is coming out to be 10 to the power minus 2 into 10 to the power minus 17, so it would become 2 into 10 to the power minus 13. So this much answer is coming. Like your carrier concentration at x equals to xn, at equilibrium the concentration was 10 to the power 4, which I am representing as Pn naught. At x equals to xn, that concentration has become so much low. So that means the concentration has gone here. But eventually, as you move along the neutral region, it will try to maintain the equilibrium. So this kind of concentration graph you will be getting. If I make it in a good manner, then this is how I will make it. And by the physics as well, it is completely explainable. By the physics as well, you can understand it. How you will be able to understand by physics? Physics says that in reverse bias, what will be happening? There will be a strong electric field. If there is strong electric field, what this strong electric field will do? The strong electric field will sweep all the electron and holes. So whatever the minority holes are present here, those will be swept because of this electric field. What this electric field will say? This electric field will say that move in this direction. Whatever the electrons are present, what this electric field will say? Move in this direction. So electric field is sweeping all the electron and holes. So inside the depletion region, what they are doing? They are reducing the concentration of electron and holes. That's why in the reverse bias, generation current would come into action. Is that understandable to you? Whatever the formula that you have studied in the forward bias, the same formula you will be getting here as well. N into P equals to Ni square e to the power Va by Vt. But Va is negative, no? This will be negative. If I say reverse bias of 5 volt, if I say reverse bias of 5 volt, what does that mean? That means Va is equals to minus 5. If I say reverse bias of minus 5 volt, what does that mean? That also means Va equals to minus 5 only. Like in the examination, they can say reverse bias of 5 volt or reverse bias of minus 5 volt. Both are having the same meaning. That means you are applying a negative voltage. I derived all the formula considering Va as positive, but now Va has become negative. So here negative would come up. That means carrier concentration, all the concentration are actually going down. Previously they were going up, but now all the concentration are actually going down. Is that understandable to you? I hope it is understandable. Right? So let's not write down here in brief manner. Wherever you want to write down, here you can write down that Va would always be negative in case of reverse bias. Va. I am not talking about VR. Sir, here all these questions we solved. Here you are adding up everything. Yes, I will add up everything because I know that depletion width is actually getting increased. So with the built-in potential, some potential is being added. So this is a complete different scenario. But wherever in any question, I equals to I naught e to the power Va by Vt minus 1. This formula we derived for the current in the forward bias. The same formula will be there for current in reverse bias as well. But what will happen? Va would be negative. So we will do the discussion on this particular formula as well. But there Va would be negative. If Va is negative, what will happen? This value will go down lesser than 1. So current would be negative. And you can see that current is flowing in the opposite direction. In forward bias, the current was flowing in this direction. In reverse bias, current is flowing in this direction. So all this discussion we are going to do. But as of now, what you need to understand, that same formula would be there, just Va would be negative. So carrier concentration plot would go like this, and you know that device will try to maintain its equilibrium. So as you move along the N side, as you move along the neutral N side, eventually your equilibrium condition will be maintained. But near the depletion region, something else is happening. Near the depletion region, what is happening? Near the depletion region, you can see that concentration is actually going down. Whatever the concentration we had previously, that same concentration is not maintained. The concentration is going down because of this formula. So if I write down concentration of electrons on P side at x equals to minus xp, what that would be? So that would be NP naught e to the power VA by VT. So this would come out to be this much. Okay. So at the equilibrium, we were expecting concentration of electron on p side NP naught, but that has gone down drastically. So we can solve some numerical based on that. You will be able to understand. Very straightforward numerical it is. Very, very straightforward. Na, Nd, Ni square. It will not be asked in the examination. Just I am telling to explain this particular thing. Although it is understandable to everyone, but still let's do it. Okay. So under equilibrium, we are supposed to find out all the concentration. So number of electrons on p side under equilibrium. What that would be? Ni square by number of electrons on p side. Ni square by Na. So Ni square 10 to the power 10 divided by Na, that would be 10 to the power 4. Now number of electrons on n side under equilibrium. Number of electrons on n side under equilibrium. Number of electrons, that would be equal to Nd only. Right? 10 to the power 15 centimeter cube inverse. Now number of holes on n side under equilibrium. Number of holes on n side under equilibrium, that would be Ni square by Nd. So Ni square is 10 to the power 20 divided by Nd, that would be 10 to the power 5. Now number of holes on p side under equilibrium, what that would be? That would be nearly equals to Na, 10 to the power 16. Right? And under equilibrium, you can see that concentration of electron multiply with concentration of holes is equals to Ni square only. You can see that if you multiply both of them, what you are getting? 10 to the power 20, and if you multiply both of them, then also you are getting 10 to the power 20 only. Right? Now reverse bias of 0.3 is applied. Find the electron concentration as at the edge of depletion region on the p side and hole concentration at the edge of depletion region on n side. So what you need to find out? Electron concentration at the edge of depletion region on p side. On p side. On p side I need to find out. So your electron concentration on p side under equilibrium e to the power Va by Vt. You would see that sir answer would be much lesser. So electron concentration on p side under equilibrium. Electron concentration on p side under equilibrium, that would be 10 to the power 4 e to the power Va, reverse bias of minus 0.3. Although it is mentioned positive, but I will put a minus 0.3. So answer is coming out to be 0.3 upon 0.026 plus minus e to the power. So 9.47 into 10 power minus 6. So 9.47 into 10 to the power minus 2, which is nearly 0 only. This much electrons on p side at x equals to minus xp, this much electrons you are having, which is much lesser than this value. Right? They were already less. Now this has become very less. That means it is nearly 0. So in some books you would see that graph is starting from 0, which means that the concentration has become much lesser. Number of holes on n side at x equals to xn. That would be number of holes on n side under equilibrium e to the power Va by Vt. So 10 to the power 5 e to the power minus Va by Vt. So answer would simply be 9.47 into 10 to the power minus 1. So again this is also much lesser. Okay. So although it will not be asked in the examination, just to explain this particular plot, we have written down this calculation. Not very important. For forward bias it is important. In forward bias they can frame the same question. They will just write down for a forward bias of 0.3 volt, find out all these values. So here e to the power 0.3 divided by 0.026. So the value will be different, right? The value will be increased. So this kind of question for forward bias also we have seen. Now for the reverse bias also we are going to see. So that we have seen. But in the forward bias we derived the expression, we did the derivation as well, everything we did. But here directly we are seeing it. Okay. Well and good. Now sir, ideally you should teach current equation. This was the flow of forward bias. That sir, you started teaching carrier concentration, then you went to current characteristics, then you went to ideal, non-ideal current characteristics. So ideally I should teach this, but we will focus on more important part, and the more important part is capacitance. So whether it is a forward bias or it is a reverse bias, in PN junction there will be some capacitance. Why there will be some capacitance? What is the reason behind that? So now we are going to discuss about capacitance, but what is left? Current equation is left, sir. Current behavior is left. which you are leaving for further time. Okay, so once we are done with this particular topic, then we will move towards the current equation. So as of now, we are ignoring this current equation because it is not that important. Surely it is important, but it is very straightforward because I already know the formula. From the formula, I will be able to understand within 15 minutes. And then we will understand a non-ideal current equation as well. Because ideal current equation for reverse bias we will understand, then we will understand non-ideal current equation in the reverse bias. That is actually an important topic. This is actually an important topic. Okay, so this we will understand and this we will understand, but later on in the next lecture. As of now, what we are understanding? We are understanding about the capacitance. So whether it is forward bias or reverse bias, the PN junction will have some capacitance. Why is that so? So let's understand that. So what is actually a capacitor? In capacitor, there will be two conducting plate. On one of the side, there will be positive charge. On the other side, there will be equal and opposite negative charge. So if I am having Q charge here, on the other side, I will have minus Q charge. Now across this capacitor, if I apply some bias, what will happen? Let's just say previously the bias was V. Now I have, because of this V bias, plus Q and minus Q charge was stored. Now if the applied bias has become V plus delta V, then what will happen? The charge would become Q plus delta Q, and here as well minus Q plus delta Q. That means if you change the supply across the capacitor, then the charge stored would also change. Then the value of capacitance is given by dq by dV, right? In place of delta, I could have put d as well. Like if I am doing the small change in the bias across the capacitor, then there is small change in the charge across the capacitor as well. So this is something that happens in the capacitor. Can you understand the same scenario in PN junction as well? Surely, sir. The same scenario is happening in PN junction as well. What is our PN junction? Sir, this is our PN junction under equilibrium. And if I apply a reverse bias, what will happen? The depletion width will change. First, let's understand that how PN junction acts as a capacitor, and then we will talk about the capacitance value. But first, our target is that how a PN junction diode acting as a capacitor. Okay, so let's understand that particular scenario. So we will see the PN junction in 3D. So this is how PN junction would look in 3D. This is your P side and this is your N side. So can you imagine now? This particular part is the neutral part, and this particular part is the neutral part. And you know that this particular part is having very less resistance, right? High resistivity. It is having high resistivity because there are charge carrier present. That means, can it work as a conducting plate? It has been written. Parallel plates are, this particular part is working as a conducting plate. This particular part is working as a conducting plate. So here I saw this is a conducting plate. This is a conducting plate. So if you see on the top level, a PN junction, you see this particular part is working as a conducting plate. This particular part is also working as a conducting plate. And on this conducting plate, on one side there is negative charge present, on other side there is positive charge present. And this positive charge and negative charge will be equal to each other because of the charge neutrality. Right? Whatever the positive amount of charge you are having, the same amount of negative charge also you will have. Along with that, there is some width also present. Like in the capacitance, here there is some, in this width, what is present? Some dielectric material is present. So here as well, in this width, some dielectric material present, that is the silicon semiconductor. Like how did you make it? There was a silicon semiconductor, then you did the doping of N side, then you did the doping of P side. So two conducting plate, one is negatively charged, one is positively charged. Inside there is some material. They are separated by some material. So that means now your PN junction is actually working as a capacitor. So this is written. Parallel plates are there, which is neutral and P region. Width is depletion width W. Charge is depletion charge. On the capacitors, we are having some depletion charge. Sorry, on these plates, if I assume these as a plate only, so on these plates we are having some depletion charge as well, and whatever the dielectric between there, that is our dielectric material. Okay, and based on this only, there was another formula of capacitor. What that was? Epsilon A by this width W. I hope you remember this formula. Okay. Now what will happen if I give a reverse bias to it? So let's just say at a particular reverse bias, at some particular reverse bias, you are having some width here. This is your minus XP and this is your XN. This is at a particular reverse bias. At VA equals to VR you are getting Xn and minus Xp. That means on this plate, how much charge is there? On this plate, the charge there is Q and dxn, and on this plate, how much charge is there? Q and xn. This is your charge per unit area. If I need to find out the total charge, then I have to multiply with the area as well. So towards this side, on this particular plate, or if you see in 3D, on this particular plate, sir, this much charge is there. Q and dxn was there, charge per unit area. If I need to find out on this particular plate only, so this particular plate is having a cross section area of A, so I multiply with A. So on this particular plate, I am having this much of charge. On this particular plate, I am having this much of charge. On the other plate, like here, I am having Q and xn, multiply with area, so this much charge is there, and on this particular plate, I am having this much of charge. Is that clear to you? Now, if I increase the bias, VR plus delta VR, or let's write down VR plus dVR. Okay. So if I increase the bias, then what will happen? The depletion width will increase. Xn would become what will happen is that Xn would become Xn plus dxn, and Xp would become Xp plus dxp. That means their charge stored will also change. So that would become AQ and D Xn plus dxn, and this would become AQ NA. This is XP. AQ NA XP plus DXP. Say yes or no? So what is the change in the charge? Previously I was having this much of charge, now I am having this much of charge. So what is the change in the charge? Because what I need to derive, I need to derive the formula of change in the charge with respect to change in the supply. So what is the change in the supply? Sir, change in the supply is this much. What is the change in the charge? So change in the charge is, what is the change? So I can see that, sir, change is Q and D dxn, or here you can say it is Q and A dxp. So I got the value of dq, and I already know the value of dv. So if I find out the capacitance applying a reverse bias of VR, what will be your, this is known as transition or depletion capacitance, because of the depletion width it is coming, no? Like why this capacitance is coming? Because of the depletion width. So this is known as your transition or depletion capacitance, or you can say that, sir, it is found out in the reverse bias. This we are finding out in reverse bias. After some time we will find out in the forward bias as well. In forward bias, what will happen? Charge injection will take place. From P side, some charge would come up. From N side, some charge will come up. So because of the charge injection as well, the total charge here will change. So because of that as well, capacitance would come into action. But as of now, we are only seeing the effect of a depletion region. That's why it is known as depletion capacitance. So that would be dq by dv. Can I write it down in this manner? Sir, what was my dq? So either I write down this expression or I write down this expression. So that would come out to be Q and D dxn divided by dvr. Okay. Now derivation is not important. I will just tell you that how you can do the derivation. So what is your xn? Sir, xn is W Na upon Na plus Nd. So you can put this value, then what they would ask, dw by dvr. So what is w? So w is 2 epsilon by q, 1 upon Na plus Nd into V built in plus Vr. Okay. So you will put these values, all these things you will do. Yeah, here one more thing, like I forgot to multiply with the area. Multiply with the area. Multiply with the area. So here also multiply with the area. Okay. So here you will put a V built in plus Vr. So you will do all these things. You will put the value of W here, then you will put the value of Xn here, then you will do the differentiation with respect to Vr. Like this can be differentiated, right? This you can find out. So some value you can find out, that value you can put here, and from here you will put the values. Eventually you will get the answer. The answer would come out to be epsilon A divided by W. That's it. Where W is W depletion. So let's write down in better manner. So your transition capacitance is coming out to be epsilon A divided by W depletion, depletion width. So depletion width under what kind of biasing that you have applied, this kind of formula you will be getting, where depletion width will be this much. This is our depletion width, where W depletion is. So derivation is actually not important, but a lot of questions will be framed only from this formula. Only formula based question would be there. So that's why we are ignoring the derivation as of now. So 2 epsilon by Q 1 upon Na plus 1 upon Nd V built in plus Br. So eventually when you solve this particular scenario, this is the answer that you will be getting, right? And one thing you already know, what do you know? That sir, W depletion is proportional to V built in plus Vr. And sometimes V built in plus Vr is known as junction potential as well. Okay. Sometimes it is known as junction potential. What is the total junction potential? Total junction potential is nothing but Vr plus V built in only. Reverse bias along with the built in potential. So from here, what did you understand? That your transition capacitance is inversely proportional to W depletion, and that is proportional to V built in plus Vr. So from here I can see that my transition capacitance is inversely proportional to under root V built in plus Vr. A very important result. I don't know why, but a lot of numerical questions have been asked in GATE examination from this particular relation only. They will give you a particular value of V built in, then they will ask you, then they will say that at this much of reverse bias, this much of transition capacitance we are getting, then at this much of reverse bias, how much transition capacitance we will get. So we will solve that kind of numerical, but very straightforward numerical they are, very straightforward. Only the formula of transition capacitance you need to remember, that is epsilon A by W, which you already remember, right? Capacitance formula, epsilon A by W, that we already remember. Then W depletion, what is the formula of W depletion? W depletion would depend on V built in plus Vr. Then W depletion is simply proportional to V built in under root V built in plus Vr, and then if I put here, then I get this expression. Okay, so the same thing has been written here, but we don't need to care about it. So let's simply solve the numerical. So this kind of numerical can be asked in the examination. What they are saying, for an abrupt junction, built-in potential is given, reverse bias of 0.7 is applied. Built-in potential is 0.3. First you are applying the reverse bias of 0.7, then you are applying the reverse bias of 3.7. When you apply the reverse bias of 0.7, then the depletion capacitance or transition capacitance was found to be 1 picofarad. So your transition capacitance was found to be 1 picofarad, and you know that transition capacitance is inversely proportional to this particular thing. So first our V built in plus VR1 value was 0.7 plus 0.3, that was 1 volt, and then this value became 3.7 plus 0.3, then this value became 4 volt. Okay, so transition capacitance at this much of reverse bias, that would be proportional to 1 by 4 volt, and the transition capacitance, this I am calling as CT2. Transition capacitance as at reverse bias of this much, that will be proportional to 0.7 plus 0.3, that would be 1, right? So transition capacitance when 3.7 reverse bias is there, that is proportional to under root 4. When 0.7 reverse bias is there, that will be proportional to 1. Okay, so this is the answer we are getting from here. CT2 is CT1 under root 1 by 4, that is 1 by 2. So what is CT1? CT1 is 1 picofarad divided by 2. Answer would be 0.5 picofarad. This is the answer. Okay, very straightforward question it is. Like, don't even feel like that, sir, it is difficult. Just inverse proportion relation is there, you will be able to find out. Just make sure one thing, that never ever forget V built in. If it is mentioned, then take it into action. 0.3 plus 0.7, that would become 1, and 0.3 plus 3.7, that would become 4. So under root 1 by 4, just inverse proportion is there, right? So if reverse bias is increased, then transition capacitance would go down, right? So what kind of graph you will be getting? If I make the graph with respect to the reverse bias, transition capacitance with respect to reverse bias, if I make the graph, So if reverse bias is increasing, transition capacitance goes down. So this kind of graph you will be getting. Okay, and at zero reverse bias there will be some kind of transition capacitance. So this kind of graph you will be getting. Okay, this graph with respect to the reverse bias. So I need to change the slide. I will take some break as well. So when we restart, we will study about diffusion capacitance. In forward bias as well, some capacitance would come into action. Sir, we were studying about reverse bias, sir. Why suddenly forward bias is coming? Since we are discussing about the capacitance, so I will discuss that capacitance in the forward bias as well. So in forward bias, because of the charge injection, some capacitance would come into action, and that is known as diffusion capacitance. So that we are going to discuss, and then we will show like 3 to 4 numericals based on only capacitance. Okay, based on only capacitance, we are going to see 3 to 4 numericals. Well and good. Okay, so let me change the slide and then I will come back. Yeah, welcome back. So we have been studying about the capacitance. So first we studied about the transition capacitance or depletion capacitance. Now there is another capacitance that is known as diffusion capacitance. So when I apply a reverse bias, when I apply a forward bias, what will happen? In the forward bias, a lot of holes from the P side will be injected towards the N side, and a lot of electrons from the N side will be injected towards the P side. Like this kind of scenario we will be getting, that here these are your excess holes on N side, and here you will be getting excess electrons on P side. Now if I increase the forward bias, previously I applied VA, now I have applied VA plus delta VA. So if I increase the forward bias, then what will happen? More and more holes from the P side will be injected towards the N side, and more electrons from the N side will be injected towards the P side. So if you increase the forward bias, then hole injection is also increasing. So this was the previous scenario. This was your previous scenario, like I am making with respect to length L. Okay, like with respect to the complete length of N side, I am making this particular diagram because you know that with respect to the length, they will start recombining. But if I increase the forward bias, then what will happen? More and more holes will come into action, and the graph would go somewhat like this. And similar thing would be happening here as well, right? Similar thing would be happening this side as well. So simple conclusion is, if you increase the forward bias, the minority excess carrier concentration is increasing. That means if I am changing the voltage, the charge is changing. How charge? Because more holes, that means more positive charge. More electrons means more negative charge. So if I am changing the voltage, charge is changing. What does that mean? Capacitance is there. Okay, so another capacitance is coming into action, and that is known as diffusion capacitance. So diffusion capacitance is the capacitance that is appearing in the forward bias due to the storage of minority charge carriers in the neutral region of the P and N junction, right? In the neutral region of P and N junction, we are storing minority charge carriers. Like on the N side, we are storing excess holes, and on the P side, we are storing excess electrons. It is called diffusion capacitance because the stored charge are mainly the result of a carrier diffusion, right? You already understand the meaning of this line, right? Because of the diffusion only, holes are coming from the P side to N side, and electrons are going from the N side to P side because of the diffusion only, because depletion width has reduced. Previously the depletion width was minus xp naught and xn naught, but now it has become minus xp and xp. Applying the forward bias, the depletion width has reduced, and more holes are going from P side to N side, and more electrons are going from N side to P side. So because of that, there is some capacitance that is coming into action, and that capacitance is known as diffusion capacitance. Okay, so what is the formula of diffusion capacitance? CD, directly we are writing down the formula. Derivation is not important at all. Okay, so formula of diffusion capacitance is tau I by neta Vt. Will you be able to remember it? Tau I by neta Vt. What is tau here? Tau is nothing but carrier lifetime. Carrier lifetime. Basically, lifetime of electrons equals to lifetime of holes equals to tau. Sir, what if their lifetime is given different? Then this tau value is given by tau n in plus tau p ip divided by in plus ip. You don't need to mug it up, okay? I am pretty sure if the question is coming on diffusion capacitance, then they will give tau same only, but it is not tough to remember, right? Tau n in plus tau p ip divided by in plus ip. In is the current in the forward bias because of the electron. Ip is the current in the forward bias because of the holes. right? I don't need to write down what is I and what is IP. I hope it is very much understandable to you. Okay, so tau n is like the average, like it is like a average only, no? We are calculating average only. Tau n IN plus tau p IP divided by IN plus IP. So tau is nothing but the carrier lifetime. So what is the diffusion capacitance? Diffusion capacitance is nothing but tau I divided by neta Vt. From where this formula came, you don't need to worry about that. Just simply remember it. How will you remember? Sir, Q by V. This is what we remember, right? Q by V. Right? This is the value of capacitance. Now what is Q? Sir, I equals to dq by dt. So from here I can remember that Q is nothing but current into time. So current is I, time could be tau. Because what will be the unit of carrier lifetime? That would be second only. Unit will be second only. So tau I divided by voltage. What kind of voltage we remember? Thermal voltage. And neta is something that would also come up. Neta could be 1 or 2. Neta could be either 1 or 2. Neta is what? Neta is ideality factor. So here I am just mentioning that what is neta. Neta is ideality factor. So I hope it is not tough to remember. Very simple. Tau I by neta Vt. Now you know that in the reverse bias the current will be very low, and we will prove it as well. So if I write down the formula here, what will be my CD? CD would be I naught e to the power Va by Vt minus 1 e to the power Va by Vt minus 1 divided by eta Vt. Okay, in place of I, what I have put, I naught e to the power Va by Vt minus 1. That means it would rise exponentially. So this kind of graph you will be getting. Exponential rise. Is that clear to you? Even this I naught value will be very low actually. So basically the graph would be somewhat like this, like till a certain point it would be very low. I will make it somewhat like this, like till a certain point it is very low, and after that it would rise exponentially. Like till this point it is actually very low, and then will rise very fastly. Why is that so? Because this value will become very large so that you would be able to ignore 1. Basically we have talked about this expression, no? This expression is always not exponential. There is this 1 as well, but at some certain voltage this 1 will be ignorable, then it would rise exponentially. So this kind of graph you would be getting. That means after a certain point it would rise exponentially. So this is your diffusion capacitance. Okay, so there is nothing in this particular topic. First we studied about transition capacitance, or we call it depletion capacitance, and then we studied about diffusion capacitance. Only thing you need to remember is formula. That's it. 2 formula are there. Those formula if you remember, your job is done. And we will solve a lot of numerical problems, and you will realize that what kind of questions are asked. Very simple questions are asked, but they are important. Simple but important. Okay, so what is the formula of diffusion capacitance? Only thing I need to remember, tau I by neta Vt. And what is the formula of transition capacitance? Epsilon A by W. That's it. This is something I need to remember. And your transition capacitance or depletion capacitance is inversely proportional to W, and W is proportional to VR plus V built in. That's it. If you only remember this particular thing, your job is done. You will be able to solve 99.99% of the numericals. Let's get started. First question. Uniformly doped semiconductor PN junction is there at 300 Kelvin. Junction capacitance. What they have talked about? Junction capacitance. What is the meaning of junction capacitance? Like it could be transition capacitance as well, or it could be diffusion capacitance as well. It could be both. Okay. But what they are talking about? Reverse bias. When we talk about reverse bias, that means they are talking about transition capacitance. They can simply mention junction capacitance. Now from the junction capacitance, you need to think whether it is transition or diffusion. So if reverse bias is mentioned, you need to think of transition capacitance or depletion capacitance. If forward bias is mentioned, you need to think of diffusion capacitance. Okay, all fine. So junction capacitance at 0 bias is shown by Cj0, and junction capacitance at a 10 volt reverse bias is shown by Cj10, and the ratio is given 3.13. Under reverse bias, the space charge width in the P region is 0.2 of the total width. Find the P side doping concentration. Na you need to find out. So first thing from here, what I can see that P in the P region depletion width is 0.2 of the total width. What does that mean? That XP is 0.2 times of whole width. So from here, what is this whole width? 0.2 xn plus xp, right? So from here, can you let me know one thing? What is Xn ratio Xp? It would come out to be 0.8 ratio 0.2, and that would come out to be 4 ratio 1. This is your Xn ratio Xp. Say yes or no? So what will be your Nd ratio Na? That would be 1 ratio 4. Very simple thing, right? So what will be your Nd by Na? Nd by Na, from here only I can see it is 1 by 4. So Nd can simply be replaced by 0.25 Na. Nd can simply be replaced by 0.25 Na. Why we have written down so? Why it is important for us? Because what we need to find out? We need to find out the value of Na, no? So it would be easy for me. Now I need to find out the value of Na. So somewhere wherever Nd would be written, I will be able to replace it. Okay. Now what all information is given? This particular information is given. Under a certain reverse bias is also not mentioned. So you know that, okay, reverse bias is mentioned 10 volt. Now you know that this junction capacitance or transition capacitance is inversely proportional to this particular thing, right? So what I can see, under root V built in is not mentioned, under root V built in plus 0 bias divided by under root, what is mentioned, Cj0 divided by Cj10. That means Cj0 will be inversely proportional to V built in and Cj10 will be inversely proportional to V built in plus 10. So are you able to understand this point that, sir, I am writing down this particular thing? V built in plus 10, V built in plus 0 is equal to 3.13. Say yes or no? Right? So you can solve it from here. V built in plus 10 divided by V built in 3.13 whole square. (3.13) whole square (9.79) minus 1 reciprocal and then 10 minus 1 reciprocal and then 10. So whatever the calculation you need to do, from here you can do the calculation. V built in is actually coming out to be 1.136 volt. This is the V built in value we are getting. Okay, very easy calculation, you can do it. How did I write it down? From here only, that Cj0 ratio Cj10 is given. So it would be inversely proportional to 0 bias, inversely proportional to 10 bias. Under root sign is already there. So V built in we have got. Now I know that what is the formula of V built in? V built in is nothing but Kt ln Na by Ni square. So this is the beauty of EDC, that if you know whatever that you know, if you write down whatever that you know, then you will be able to solve the problem. Like, this is the beauty of EDC. You would be able to solve the problem if you just keep on writing down everything that you know, and then you would realize that I am getting to the answer. If you just read the question, it would feel like that, sir, this information is given, that information is given, but every information will be used once you write down the formula and everything that you know. Okay, so now V built in I already know, that would be 0. Kt value they have mentioned, no, they did not mention it, so 0.0259 I will take ln Na and D. So it would become 0.25 Na square, right? Because Nd is 0.25 Na, so it would become 0.25 Na square divided by Ni square. So Ni square would be 1.8 square into 10 to the power 12. Okay. So 1.136 divided by 0.0259. Then exponential into 1.8 into 1.8 and divided by 0.25. 10 to the power 32. So 1.449. Just you take the under root. So here I will be getting 10 to the power 32. That would be 10 to the power 16. So just take the under root. 1.449. 1.2. So 1.2 into 10 power 16. Yeah. So you are getting 1.2 into 10 power 16. This calculation you need to do, but do it with patience. Okay. Because under root you need to take. Wherever we need to take under root, I will just make sure that inside the under root I will always get the even power. Let's just say somewhere if I was getting 10 to the power 21, what I would do? 10 into 10 to the power 10. I will take out 10 to the power 20 outside. Okay. So 1.2 into 10 to the power 16 centimeter cube inverse. This is the doping of acceptor atom. Okay, very simple formula based questions are there, not much of concept. It's just that from here, from this particular portion, numerical problems can be framed. That's why this becomes a that's why this becomes an important topic for gate examination. Otherwise, this topic is actually very easy. It's just that numerical problems are framed. Okay, let's go to this one. Again a very simple numerical problem. P plus N junction is there. Na and D value is given. Area is given. Inductance is given in parallel with the junction. Reverse bias is given. Calculate the resonant frequency. What do you think? What will be the resonance frequency? If you have studied basics of network analysis, if you don't know, then I am telling you the formula of resonant frequency, that is 1 by under root LC. Okay, this is the formula of resonant frequency. Actually, a diode can be replaced in small signal model. It can be replaced by its small signal resistance and the junction capacitance. Okay, this is the small signal model of diode. What is RD there? In analog electronics you will learn it. Okay, here I am writing down in analog electronics. In analog electronics you will learn it. What is small signal model? You don't even know, but I am just telling RD is neta Vt upon I. Okay, and CJ you already know. Junction capacitance could be diffusion capacitance or transition capacitance. But here transition capacitance is coming into action because reverse bias is mentioned. That means we are talking about transition capacitance. Okay, so here I will ignore this particular part. Only CT would come into action, transition capacitance would come into action. Okay, and RD is neta Vt upon I. From where this formula came, sir, we will understand in analog electronics. But as of now in this question, inductor value is mentioned. Your target is just to find out that transition capacitance. That's it. If I am able to find out the transition capacitance, my job is done. Okay, so what I need to find out? Transition capacitance. What that would be equivalent to? Epsilon A by W. Am I given the value of epsilon? Yes. Am I given the value of A? Yes. Am I given the value of W? No. So I need to find out the value of W. What that would be? Under root 2 epsilon by Q. 1 upon Na plus 1 upon Nd. Can I ignore 1 upon Na? Yes. Why is that so? Because Na is much greater than Nd. So 1 upon Na could be ignored. Into V built in. V built in is mentioned? No. So you need to find out V built in as well. Okay. So again a lot of calculation, nothing else. So what will be V built in? Sir, Vt ln. So I will not apply the formula. I will directly write down the values. 0.0258 ln Na and D by Ni square. Na and D, that would become 10 to the power 33 divided by Ni square. 10 to the power 33 divided by Ni square. Right? 10 to the power 18, 10 to the power 15. So that would become 10 to the power 33 divided by 10 to the power 20. So 10 to the power 13 ln into 0.02585. So 0.77. 0.7737 volt. Okay, so let's write down here. Now 2 epsilon by Q. 2 epsilon value 11.7 8.85 into 10 to the power minus 14 divided by Q, 1.6 into 10 to the power minus 19. What is the value of Na? Na, sorry, not Na, Na is very much larger, no? So it would be Nd, not Na. What is the value of Nd? That is 10 to the power 15. And what is the value of built-in potential that you are getting? 0.737. Oh, sorry, 7737. So let's see what is the depletion width we are getting. So 10 to the power, everything is going in centimeter. Just remember, everything is going in centimeter. So this is 10 to the power 10 to the power minus 10. So it would become 10 to the power minus 5 outside. So whatever the answer we are getting here, into 8.85 into 2 into 11.7 divided by 1.6. Then you take the under root. So 10 into 10 to the power minus 5 we are getting. That means 1 micrometer we are getting. So this is coming out to be 1 micrometer. Okay, so I'm getting 10 into 10 to the power minus 5. That would be 10 to the power minus 4 centimeter. 10 to the power minus 4 centimeter would be 1 micrometer only. So depletion width is coming out to be 1 micrometer. Now you need to find out the transition capacitance. So that would be again epsilon value 11.7, right? So 11.7 into 8.85 into 10 to the power minus 14. What is the area? Area is 6 into 10 to the power minus 4 and divided by W. So W as well I will write down 10 to the power minus 4 only. Why so? Because that was 1 micrometer, or you can say 10 to the power minus 4 centimeter. Every calculation is going into centimeter. Okay, so this and this will get cancelled. So 11.7 into 8.85 into 6. 11.7 into 8.85 into 6. So 6.21. 6.21. So what is the transition capacitance we are getting? 6.21. 621 here I am getting, and that is 10 to the power minus 14. So let's write down in this manner only. 621.27 into 10 to the power minus 14 farad. This is the transition capacitance we are getting. We need to find out the resonance frequency. So that would be 1 by under root LC. Under root LC. So 1 by under root. So what is the value of L? 2.2 milli. And this is 621.27 into 10 to the power minus 14. Right? So I will prefer 10 to the power minus 13 here. Why so? Why I will prefer 10 to the power minus 13 here? Because you know that I will be easily able to take out 10 to the power minus 8 outside, right? 10 to the power 13, 10 to the power 16 it would be. So 10 to the power 8 outside I will be able to take. So this would be 100 into 10 to the power 6. 10 to the power 8 I have taken outside. So 100 into 10 to the power 6 I can write down. And here in the reciprocal what I am getting 62.127 into 2.2. 62.127 into 2.2, and then take the under root, then take the reciprocal, and then multiply with 100. So 8.5. Calculation error is there. Okay. No, sorry. This is in hertz. We have find out in radian per second, right? So as of now, when I solved it, my answer is coming out to be 8.55. This error happens a lot of time with a lot of students. Our answer is mega radian per second, right? But answer could be mentioned in hertz as well. So divided by 2 pi also we need to do. So divided by 2 divided by pi, 1.36, 2.63. Some calculation error is there. Okay, huge calculation was there, no? That's why some error is there. Surely some calculation error is there. Now I don't know where I messed up. So can I leave it up to you? Like again, calculation is there. Concept and everything is fine for you. Okay. So leaving it up to you. Do the calculation on your own. Calculation self. Okay. So if answer is matching, then it is fine. If it is not matching, then it might happen that this answer is wrong. What answer I am getting? I am getting 1.36 mega. Okay. This is what I am getting, but here I answer that I have written, that is 1.63. So I am not sure which answer is correct. So you check on your own. Only the calculation part, concept and everything is fine. 1 upon under root LC. If you need to find out in hertz, then 1 upon 2 pi under root LC. Value of L is already given. C you can find out in this manner. Epsilon A by W. Oh, wait a second. This was actually a big error from our end, not minute error. What is the error? We have written down V built in here, right? Forward bias of reverse bias of 10 volt we forgot here. So that was actually a big error, not small error. Okay, so everything got mashed up here. So here 1 micrometer that I was getting, if I divide that by 0.7737 under root reciprocal, and then I multiply that with 10.7737 under root. So 3.73. Here I will be getting 3.73 into 10 to the power minus 4 centimeter. So here 3.73. So whatever the answer that I got here, divided by 3.73. 621.27. 621.27 divided by 3.73. So 166.56. 166.56. And here what I will be preferring, 16 into 656, right? So whatever 8.55 I was getting here, if I multiply this particular answer with under root 3.73, then my job would be done, right? Yes. So 3.73 under root into 8.55. So 16.51. This calculation would come out to be 16.51 and then divided by 2 pi. Yeah, 2.62. So 2.62. So that was not actually a minute mistake. This was a big error, big blunder. Okay, 2.62. So first thing is that from mega radian to megahertz, and another thing is that you never forget the reverse bias. A lot of time it happens when I was a student, it used to happen with me. As of now, I'm an educator, still I am doing this error. Okay, so never ever forget this reverse bias. Let's see this question. Like this question is not based on depletion capacitance or transition capacitance or diffusion capacitance. This is simple, like simple formula based question. But why I picked this particular question? So that you'll to let you know that some assumptions we have to take, and by default we need to take those assumptions. It might happen that in the examination those assumptions are not mentioned. What you need to find out? You need to find out that doping concentration in N region. You need to find out the value of Nd. Now maximum electric field is given. I know the formula of maximum electric field, Q Nd Xn divided by epsilon. That is given as Emax, and that is given as 10 to the power 6 volt per centimeter. Okay. Nd I can take from here, Q epsilon I already know, Xn. Now my matter of concern would be Xn. Now you would see that P plus N junction is there. If I need to find out Xn, what would be Xn? Sir, WNA upon Na plus Nd. Now sir, Na is not mentioned, only Nd is given. Oh sorry, Nd you need to find out, Na is not even mentioned. So what do I do now? P plus N junction is there, no? What does that mean? That means Na is much greater than Nd. What does that mean? That your Xp would be much lesser than Xn. That means that your W will be approximately equals to Xn only. So this assumption I will have to take. that W is approximately equals to Xn. Now what is the formula of W? Sir, 2 epsilon by Q. Now again sir, 1 upon Na would come, but from this expression what do I know? That 1 upon Na would be much lesser than 1 upon Nd. So here as well I will put the formula of 1 by Nd only. Now sir, when I write down the depletion width, here what do I require? V built in plus Vr. Sir, if I need to find out the value of V built in, I would require the value of Kt ln Na Nd by Na square. So sir, how do I get this Na value? So what you will say? V built in plus Vr. So where is the reverse bias? Reverse bias is 10. So you will have to assume that V built in is actually very low. So V built in plus Vr is approximately equals to Vr. So these many assumptions we need to take. After all these assumptions, we are getting to the answer. Are you able to understand this point? So Q Nd by epsilon, Nd we need to find out, Q epsilon I will have. In place of Xn, a lot of assumptions we have taken, and those assumptions are by default. It might happen that in the examination those assumptions are not mentioned. Only assumption is that Na is not mentioned. So whatever that is associated with Na, just ignore that. Is that clear? Okay. So 2 epsilon by Q and D. Do we have the page? Yes. Okay. Now V built in plus Vr could be mentioned as Vr only, and that is given as Emax. Okay. So you can see that somehow we can reduce it. What we are getting? Under root 2Q and D Vr divided by epsilon, that is coming out to be Emax. Okay. So from here what do you see? E square max into epsilon, E square max into epsilon divided by 2Q and D, that is coming out to be Vr. Okay, so in Jenner diode we will write down this formula there as well. In Jenner diode as well we will write down this formula, but you don't need to remember it. I have seen a lot of students remember this formula, but it doesn't make any sense. In a very simple way you will be able to write down in the answer. You will be able to write down in the examination. So don't try to mug up this formula. Okay, very straightforward formula it is. Although our matter of concern is Nd, not Vr. Okay, so matter of concern is Nd, but for the breakdown voltage, this formula a lot of students remember, but you don't need to remember it. This is what I am saying. So Nd is so what is your Nd? Nd is epsilon, that would be 8.85, but what is the value of epsilon? 12. 12 into 8.85 into 10 to the power minus 14 Emax square, that would be 10 to the power 12 divided by 2Q Vr, right? So 2Q 1.6 into 10 to the power minus 19 into Vr. What is the value of Vr? Vr is 10. So here we are getting 10 to the power minus 18. So that would become 10 to the power 4, 10 to the power 16. 10 to the power 16. So 6 into 8.85 divided by 1.6. So 10 to the power 15 there. I'm getting 10 to the power 16 only, 5, 17. 17, okay, divided by 10 there as well. Okay, fine. 3.3, 3.31. Here what we are getting? 3.3. Okay, 3.3 into 10 to the power 17 centimeter cube inverse. This is the value of Nd we are getting. Okay, very straightforward, very simple. Why you picked this question, sir? Just to let you know that this is how we can take the assumption very smartly, just because P plus N junction is mentioned. So just by using this P plus N junction, we are taking all these approximations. Okay. So wherever approximations are taken, I am just putting that in a box here as well. This is also important. Okay, and here as well, this is also important. Well and good. Okay. Find the change required in the forward bias such that the diffusion capacitance gets doubled at 300 Kelvin. What is the formula of diffusion capacitance? Tau I by neta Vt. Could be written as tau I naught e to the power Va by Vt minus 1 divided by eta Vt. Okay. Now what do you see here? That Cd is now proportional to e to the power Va by Vt minus 1. Okay. Here in the question it should be mentioned that given Va is much larger than Vt. Okay. It is given. Applied forward bias is much larger than Vt. It is given. So if this is the relation we are getting, that your diffusion capacitance is proportional to e to the power Va by Vt minus 1, because tau is a constant value, I naught is a certain value, neta Vt also certain value. Now if applied bias is very large, if this value is very large, that means one can be ignored. This one can be ignored. With respect to e to the power Va by Vt, one can be ignored because Va is very large. 20 divided by 0.026, you see the value of this one. That would be very large. Okay. So diffusion capacitance got doubled. So Cd2 divided by Cd1 would be e to the power Va2 divided by Vt, Va1 divided by Vt. So Cd2, this got doubled, right? So if this value is 2, e to the power Va2 minus Va1 divided by Vt. So Va2 minus Va1 is coming out to be 2 ln into 0.0259. So 17.9 millivolt. That means you need to increase the forward bias by 17.9 millivolt. If you increase by 17.9 millivolt, then your diffusion capacitance will get doubled. Okay. Like a very minute change I have done. Still, the diffusion capacitance is getting doubled. Why is that so? Because exponential rise is there, no? You see this diagram, exponential rise is there. So just because of the small change, only a small change I did here, only I changed by 17.9 millivolt, it is millivolt. So just by doing a very small change, I got I got the diffusion capacitance to be doubled. Fine, all good. Okay, so now this topic is also completed. Now we are going to see, one more topic is left, that is 1 by Ct square versus VR curve. What is Ct? Transition capacitance. So what we are going to do, we are going to take the reciprocal of transition capacitance, do its square and plot it versus the reverse bias. What do we get? Let's see that. Something interesting we are going to get with that particular plot. Why this plot is necessary, you will understand it. Okay. So let's first try to see what we are actually getting. What is transition capacitance? Epsilon A by W depletion. This is the formula of W depletion, under root 2 epsilon by Q, 1 upon Na plus 1 upon Nd, V built in plus Vr. What we need to do? We need to take the reciprocal and then do the square. So if I take the reciprocal 1 by Ct, what will happen if I invert it? So what you can see, this is epsilon, this is under root, right? And this is area only. So let's keep area aside, but you can see that on the upper side what you will be getting. Basically this is the scenario. This part will go upward side, 2 epsilon by Q into 1 upon Na plus 1 upon Nd into V built in plus Vr. And this part will come downward, epsilon A, right? So epsilon I can take inside, it would go as epsilon square, and 1 by A I am taking this side. Fine. Okay, this area remains here. So this and this part, what it would become? 2 by Q epsilon, and then I need to take the square on the both of the side. So 1 by Ct square, this would become 2q a square into 1 upon Na plus 1 upon Nd V built in plus Vr. This is the relation we are getting. So this is our y. This is our some constant value. Let's just say this constant value is m, right? And then this is another constant value V built in plus Vr. This is something we are getting. Say yes or no? We did nothing, it is simply mathematics, nothing else. Transition capacitance, epsilon A by W depletion, under root 2 epsilon by Q, 1 upon Na plus 1 upon Nd, V built in plus VBr, right? Now 1 upon Ct, that means the reciprocal I need to take. So this, if this part goes inside, how it would go? Epsilon square A square, right? If this part goes inside of it, inside this under root, then it would go as epsilon square A square. And then I need to take the under root as well. So I am getting 2q upon epsilon. Okay, epsilon I forgot here. Sorry guys. 2q epsilon A square. Okay, 2q epsilon A square. This epsilon and this square get cancelled out. So 2q epsilon A square 1 upon Na plus 1 upon Nd V built in plus VBr. Now this is a constant value only because this is doping, Na and D are doping. 2q value we already know, epsilon also we already know. Area, cross section area would be constant. V built in also a constant value. Now what we need to do? We need to plot, this is our x. This is our x. So y versus x plot we need to do. So what kind of plot you will be getting? It will be a linear plot, right? What we are plotting, it will be a linear plot. So what is the relation we are getting? 1 upon Ct square equals to some constant value V built in plus x. So this was our PN junction. We are applying a, what we are drawing? We are drawing 1 by Ct square versus Va. Here you wrote down, sir, 1 by Ct square plus versus Vr. So this would be my Vr. Reverse bias. If I say I am applying a reverse bias of 5 volt, then what is the value of Vr? Sir, it would be 5 volt only. If I say I am applying a reverse bias of minus 5 volt, then what will be the value of Vr? That would be 5 volt only. Here in this formula, what do? You will always add up, no? If I say I am applying a reverse bias of 5 volt, find out the depletion width. What you will do? V built in plus 5. If I say I am applying a reverse bias of minus 5 volt, what you will do? V built in plus 5. Is that clear to you? Basically, depletion width was increased, so you will add it up. So just listen to me. 1 by Ct square versus V built in plus Vr we are drawing. Here I have put V applied. Actually, you will apply it negative. Let's just say I apply, what I am going to do? V I am going to apply minus 3 volt. Right? Because P side should be connected to negative, N side should be connected to positive if I am talking about the reverse bias. So when I apply minus 3 volt, whatever the value of 1 by Ct square I get. Now if I apply it minus 4 volt, so the value of 1 by Ct square will be increased or decreased. Just let me know this particular thing. If I apply minus 3 volt, then some value I am getting. This is the value I am getting at minus 3. If I apply Va equals to minus 4 volt, then the value will increase or decrease. Va equals to minus 4 volt means you are applying a reverse bias of 4 volt. Applying a reverse bias of 4 volt here. If this value gets increased, that means Ct gets decreased. If Ct gets decreased, then this value gets increased. Or you can see here, if I am applying Va equals to minus 4 volt, Va equals to minus 4 volt simply means that I am applying a reverse bias of 4 volt. So if I put 4 volt here, V built in plus 4, that means this value will be increased, then Y will be increased. Previously I was putting 3 here. Previously my Va was minus 3. Then our reverse bias was 3 volt. So if I put 3 here, then whatever the value I get. Then if I put 4 here, then whatever the value I get. Basically for minus 3 this value I was getting, then for minus 4 this value I will get, no? And second thing I know that relation is linear. Relation is linear. So if linear relation is there, then can I get a graph somewhat like this? Say yes or no. So what I will do, I will make up this particular circuitry and then I will reverse bias this particular diode. What I would do, I would reverse bias this particular diode. Why I am not forward biasing it? Because if I forward bias, then diffusion capacitance would come into action. I don't want diffusion capacitance. I only want transition capacitance. Okay. So in the reverse bias, whose effect you can see? Only transition capacitance you see. In forward bias, who will come into action? Sir, diffusion capacitance would come into action. But what do I want to see? I only want to see the transition capacitance. So in the reverse bias, I have drawn this plot. What I am doing? First I applied zero bias, then I saw the value of transition capacitance, then I note it down, and then I saw the value of transition capacitance, then I note down the value of 1 by Ct square. Then what I did, I applied a reverse bias of minus 1 volt. Okay, reverse bias of 1 volt, you can say reverse bias of minus 1 volt. Then I got the value of transition capacitance, then I note down the value of 1 by Ct square. Then I applied minus 2 volt and I got this characteristics. Okay, so this characteristics I got for 1 by Ct square is equivalent to some constant value you got here, V built in plus VR. Now just as I got this curve, what I can do? Can I increase this curve on the previous side? Like, can I increase this curve like this? Now please note that you are not applying a forward bias voltage. Let's just say this is not that, sir, I am applying 1 volt. Here I am applying 1 volt. No. If you apply VA equals to 1 volt, what will happen? The diffusion capacitance would come into action. And the diffusion capacitance would come into action, then you will not be able to think of transition capacitance, because diffusion capacitance would be much larger. So you are actually applying from 0 to minus infinity. Practically what I am doing, that I am telling. Okay, so you are actually applying from 0 to minus infinity. You draw this graph, then you increase the graph backward. Like, you know that constant slope is there. So if I increase the graph backward, what do you think what this point would represent? This point would represent minus V built in. Say yes or no. So this is how I can measure the built-in potential of a PN junction diode. What I did, I will operate my diode in the reverse bias. When I operate my diode in the reverse bias, I will keep on getting the value of a transition capacitance. I will take its reciprocal, then I will plot it on the graph. Then I will increase the reverse bias more. I will get more values. I will plot it on the graph. I will see that I am getting a linear graph. Now what do? I will increase that graph backward and I will see where it is cutting. And the point where it cuts on x-axis, that point will be minus V built in only, because where 1 by Ct square would go 0. 1 by Ct square going to 0. What does that mean? That means your VR is coming out to be minus VBI, right? So basically this value will be minus VBI. So this particular axis is for VA, but this particular axis is for VR. If I am going in this direction, then I would say I am going for VA. If I am going in this direction, that means I am going for VR, because VR would be always positive for me. So here, if I say I am applying a VA voltage of minus 3 volt, that means I am applying a reverse bias of 3 volt, reverse bias of 4 volt, reverse bias of 5 volt, reverse bias of 6 volt, and so on, right? So VR equals to minus V built in. So this is how you can find out the value of a built-in potential. So this was the very simple concept. That's it, nothing else. So why we plotted 1 by Ct square versus VR, you understood, to find out the value of built-in potential. What kind of numerical can be asked? This kind of numerical can be asked. Okay, what they are asking, find out the built-in potential. This is the question they are asking for a P plus N diode. Now you know one thing. What do you know? That, sir, 1 by Ct square is equals to some slope V built in plus VR, right? Okay, sir. Now what thing you can do, like 1 by Ct square value I am having, so I can try finding out the value of M and I can try finding out the value of R. In this manner I can do, or what you can do is that simply you know that this line will be following the slope and you know this value is V built in. That's it. You already know that, sir, this value will be V built in. So what you do? Can you solve this equation? Like simple line equation you need to solve. What is the slope we are getting here? Can I find out the slope? Can I simply find out the slope? Yes, sir. What will be the slope? Slope will be negative. So you can see that slope will come out to be minus 2.1 into 10 to the power 23 divided by 2. 1.05 this will be the slope. Now I need to find out this particular point, V built in. How will I find it out? I know the slope of this line, no? I know the slope of this line. That slope is coming out to be this much. So if you know the slope, then your job is done. What does the slope says? Forget about the unit. Slope says y2 minus y1. y2 is 0 minus y1 2.9 into 10 to the power 23 divided by x2 minus x1. What is x2? V built in. Minus what is x1? Plus 2. There you go. Right? So V built in plus 2. What that would be? 2.9 divided by 1.05. And then minus 2. So 0.761. So from here, directly I can solve it and I'm getting 0.761. Did you understand how to solve this particular question? Very straightforward it was. Very, very straightforward. What was the problem? Only I find out the slope, like mathematics it was. You just need to know one thing, that this particular point will be representing V built in. That's it. If you know that this particular point will be representing V built in, then your job is done. So I need to find out this particular point only. Can I find it out with respect to mathematics? If this particular graph is given and I ask you what will be this point, will you be able to find out? Yes, sir. This is how I will be able to find out. Just find out the slope, see this point, and get the answer. Okay, very straightforward. Next, we will study about ideal diode current equation, and then we will study about non-ideal diode current equation. So first, let's see ideal diode current equation. Whatever the current that you got in the forward bias, the same expression is there. I naught e to the power VA by VT minus 1. Very simple and a very straightforward expression that we already know. But how to apply this in the equations, like how to understand the current here, let's do that analysis. So what I am saying, I naught is 1 nanoampere. VT value is 25 millivolt. You are applying a reverse bias of 10 millivolt, or it can be mentioned that I am applying a reverse bias of minus 10 millivolt. Your focus should not be at this minus, your focus should be here. Reverse bias I am applying. So sir, you saw the same equation for the forward bias as well. And sir, you are seeing the same equation for the reverse bias as well. Sir, what will be the difference? The difference would be VA. In forward bias, VA would be positive. In reverse bias, VA would be negative. In forward bias, VF will always be also positive, like it was also always positive. In forward bias, VR also we always take positive. Here in these expressions, you see, if I am applying a reverse bias of 5 volt, what I will say, always I will take positive. But wherever VA is there, we are always taking negative. So in the reverse bias, you just remember that wherever VA is there, we will always take negative. You don't need to mug it up. By your own, you will think, no, that's our current equation is I naught e to the power VA by VT minus 1. The same I used to do, find out in a forward bias as well. Then what will be the difference, sir? If someone says you are applying a forward bias of 10 millivolt, so I will be putting plus 10 here. If someone is saying that we are applying a reverse bias of 10 millivolt, then I will be putting minus 10 here. Then sir, here how will I remember that I will take the positive sign? In the depletion width, how will I remember? I know that in reverse bias, depletion width get increased. So if depletion width is increasing, that means this particular part has to increase only. So that's why I will take the positive sign. So there will never be confusion. Okay. So it is not confusing, right? So just don't mess it up. So reverse bias of 10 millivolt we are applying. I naught is 1 nanoampere. So what we are writing down, 1 nanoampere e to the power. Let's keep it I naught only. Let's keep it I naught only. Okay. I naught e to the power VA by VT minus 1. So 10 by 25 e to the power minus 1. So 0.49. Okay, sorry guys, sorry. Minus sign would be there. No, I am doing the same error. That's what I was thinking. So minus 0.33. Okay. What about 25? If you apply 25, then what we are getting? 0.63 minus only. And if I apply 0.1, 0.98 minus sign only. You can see that, sir, current is coming negative. In all the cases, you can see this was the current in the first case, this was the current in the second case, this is the current here. What about this one? When VA is 0.5 volt, so 0.5 divided by 0.025 plus minus exponential. So this would be nearly I naught only, you can check. Okay, and if you apply 0.6 volt, then also it will be I naught only, minus I naught, sorry, because e to the power minus 0.5 divided by 0.025, what it is coming out to be? 0.5 it is coming out to be 2.06 into 10 to the power minus 9, which is much lesser than 1. So if it is much lesser than 1, then that means this value can be ignored. So as you keep on increasing the value of as you keep on increasing the reverse bias, what do you think? What do you see? The value is becoming nearly constant to I naught only. So what kind of graph you are seeing? Sir, initially it was rising up like this. Initially it was rising up like this, and then it is nearly becoming I naught only. Say yes or no. So this kind of characteristics we are getting. Can anyone explain that, sir, first why you made it linear and then, sir, you made it this curvature? Can anyone think of it? Why I made the characteristics like this? And secondly, you know that I naught would be negative, right? This I naught current, that would be negative. And now can you justify that why I naught was called as reverse saturation current? I naught was called as reverse saturation current because eventually in the reverse bias, your current gets saturated at I naught. Your current doesn't get increased more than I naught. Eventually in the reverse bias, your current gets saturated at I naught. That's why I naught was called as reverse saturation current. But this I naught is having no relation with reverse current. Okay, reverse current and reverse saturation current both are different. This is known as reverse current. This I is known as reverse current. This I is known as reverse current. Reverse current. But it is called, I naught is called reverse saturation current because in the reverse bias, eventually your current is being saturated to minus I naught. Can anyone tell that, sir, why you made the characteristic like this? Like first a bit linear and then bit curvature and then goes like this. It is related with basic semiconductor physics. In basic semiconductor physics, what we saw? For drift current versus voltage, what kind of curve was there? Like linear, this and then this. How did we get this current? Sir, you said that I would be sigma E, that means NQ mu E, area would also be there. And you know that, sir, this particular thing is nothing but VD. That means I is proportional to VD. And sir, what about the applied voltage? That is proportional to E. So I versus V was actually your VD versus E. So we were actually drawing VD versus E. And what was the VD versus E curve? Initially proportional, then mu to the power minus 1 by 2, and then mu to the power minus 1, right? VD versus E curve. So whenever drift current is into the action, you will get this kind of curve. Linear, some curvature, and then flat. So whenever drift current is into the action. In forward bias, we used to get this kind of curve. So in forward bias, drift current was not into the action. Who was into the action in the forward bias? In forward bias, exponential current was there. But in the reverse bias, you know that majority current, what was the region of majority current? Depletion width got increased. Because of the increased depletion width, there was very high electric field. And because of this very high electric field, minority electron and holes were moving. Although the current was very less, but that current was drift current only. And you can see that this kind of curvature we are getting. Okay, very deep thing these are. No one will ask you. Even in the interviews, no one will ask you that why we are getting this kind of curve. But If you think deeply, then this is something that you will understand, that why this kind of curvature is there. It is related with basic semiconductor physics. Okay. So what did you get to know? That in reverse bias, whenever I apply the formula, I will just make sure one thing, that VA would also be negative and my current would also come out to be negative only. Current is coming out to be negative only, no, everywhere. So current will also be coming out to be negative. That's just either you remember this thing or it would be very obvious as well. Why it is obvious? If you take VA negative, do you know the graph of e to the power x? If x is positive, at x equals to 0, value is 1. At x equals to infinity, this value will be there. If x is negative, then this kind of graph you will be getting. Like, what is the minimum value of e to the power x? So that is 0. What is the maximum value of e to the power x? That is infinity. That means if x is negative, if VA is negative, then e to the power VA by VT, it would be between 0 to 1 only. Is it obvious or not? Like e to the power x, again and again we discuss in electronics. EDC might be your first subject, EDC might be your last subject as well. You might have heard of e to the power x. Again and again in mathematics or in signal system, wherever you go, we discuss a lot about e to the power x. So if x is negative, that means the value will take from 0 to 1. So e to the power VA by VT would be there between 0 to 1. So if it is between 0 to 1, surely the current will come out to be negative only, no? Right? It is pretty obvious. So what could be the minimum value of e to the power VA by VT? That would be 0. So 0 minus 1 would be minus I naught only. So the current can go from minus I naught, right? From minus I naught to 0. Any value it can take. So this is the ideal characteristic we are having. You understood very important thing, that VA negative I will have to take, and the current I would itself come out to be negative only. Solve this numerical. Solve this numerical problem. Find out the magnitude of reverse bias voltage required to reach the 75% of its reverse saturation current. So what amount of current I require? Sir, 0.75 I naught. Is it correct? No, negative sign. Because you know that in the reverse bias, this is the characteristics. Negative voltage along with that negative current as well. Always I will get the negative current in the reverse bias. What is the meaning of negative current? Just because of the formula we are putting negative. Negative current means it is flowing from N to P. Right? In forward bias, the current was flowing from P to N. In reverse bias, the current will be flowing from N to P only, because battery is connected like this. Battery is connected like this. So current is flowing from N to P. So the formula we wrote down considering current in this direction. Right? But eventually we are using the same formula, that means current negative I will have to use. Is that understandable to you or not? Surely it is understandable. So minus 0.75 I naught, this is something that I will have to use, and that would be equivalent to I naught e to the power VA by VT minus 1. Now you would see that, sir, by default my VA is coming negative only, and it should come negative. Why is that so? Because reverse bias. Is that understandable to you? Okay. So a lot of time I have seen that people mess it up here. They would apply 0.75 I naught. They will forget this negative sign. And if they forget this negative sign, the complete answer would be different. And that answer would be wrong. Reverse bias. Always consider reverse bias. This question could have been asked for forward bias as well. In forward bias, I would take the current to be positive. Okay. So what you see? Minus 0.75. I naught get cancelled out. E to the power VA by VT minus 1. So VA is coming out to be 0.25 ln into 0.0259. So 35.9 millivolt. So minus 35.9 millivolt. But what they are asking, magnitude. Okay. So magnitude of reverse bias is 35.9 millivolt. So I hope you will remember that. You don't need to remember it. You don't need to mug it up. Simple concept is there. Just remember this characteristics. Okay. So if we draw the ideal characteristics of a diode only, for the complete diode, if I am drawing the characteristics, what is the characteristics? So this kind of characteristics we are getting, that here exponential response was there, and in this scenario very minute current was flowing, very less current only, and then a bit of curvature, this kind of current was there, and this current was nothing but minus I naught. Okay, and both of them are following the same equation only. This current is nothing but minus I naught. Okay, this is your current I versus V, and both of these curves, this is in the forward bias. I should not say V, it is VA. This is in the forward bias, this is in the reverse bias, and both of them are following this particular equation only, I naught e to the power VA by VT minus 1. So this is your ideal characteristics, ideal diode characteristics. Okay, for reverse bias, what do you think? What will be the value of e to the power VA by VT? I told you it would be between 0 to 1. Here I talked about the graph, right? E to the power x graph. So it would be between 0 to 1 because VA would be negative. So for the reverse bias, what do I know? For reverse bias, I know that, sir, VA would be negative. That means e to the power VA by VT would be between 0 to 1. Okay. So what will be the formula of current? This will be the formula of current. So always I will use this formula. In the forward bias, what will happen? E to the power VA by VT would be between 1 to infinity, right? Because VA is positive here. So e to the power VA by VT would be between 1 to infinity. Now you know that for high VA, what will happen? E to the power VA by VT would be much greater than 1. Basically, what is the formula? In the forward bias as well, the same formula of current is there. What is the formula? Sir, this formula is there. I naught e to the power VA by VT minus 1. This formula is there, sir, very simple formula. I have applied this formula again and again in the previous video. I naught e to the power VA by VT minus 1. But if VA is very high, then what will happen? E to the power VA by VT would be very greater than 1. Then this current equation also you can use. So sometimes you will find out that this current equation has been written. I naught e to the power VA by VT, but this will use only, this you will use only in forward bias. But in the reverse bias, never ever forget this one. Okay. In forward bias, if you are forgetting this one, then it is fine. Because at the higher value of VA, this one can be forgotten. Because this one can be ignored. But in the reverse bias, this one can never be ignored. So people usually remember this formula and they apply the same formula in the reverse bias as well. And everything gets matched up. Are you able to understand this point? In the reverse bias, you are never going to forget this one because e to the power VA by VT is between 0 to 1 only. So this one will always be comparable to e to the power VA by VT. But in the forward bias, sometimes you can ignore it. So that's why I wrote this note here. What is the note? That never ever ignore 1 in case of reverse bias. In case of forward bias, you can ignore this one. Okay. When you can ignore this one? In case of forward bias, this one could be ignored. Only when VA is very high. If they have mentioned VA to be very low, like if VA is comparable to VT, high VA means VA is much higher than VT. Okay. But if VA is comparable to VT, then this value will not be that large. If this value is not that large, then it would be comparable with 1 as well. So 1 you cannot ignore. Okay. So this kind of characteristics we are getting. Right. Now we need to study the non-ideal behavior. This was your ideal behavior that we have already seen. Now we are going to study non-ideal behavior, but I need to take some break. Okay. I will take some break, drink some water, and then we will study about non-ideal behavior of a diode under reverse bias. Okay. So I hope you are enjoying this lecture. Very straightforward lecture it is, not very complex. Nothing is complex here. So let's understand about non-ideal behavior of a diode under reverse bias in the next half of this video. Okay. Yeah. Thank you. Yeah. Welcome back. So now we need to study about non-ideal behavior of a reverse biased diode. Okay. So this was your ideal behavior. The current would rise up linearly, very low current, right? The current is actually very low. It would rise up linearly. Then some curvature would be there and nearly it would become constant. Okay. So it would become nearly constant at minus I naught. Although we are showing it good enough current. Again, the diagram you might feel like that, sir, this current is good enough, but this current is actually very low. Reverse saturation current, I note that is actually very low. So very low current is flowing, but you can see like in the mid voltage region, like I should not say mid voltage, in the low voltage region, it is rising linearly and some curvature is there, and after that it is becoming nearly constant. Okay. So this was the scenario of ideal characteristics. In non-ideal characteristics, what will happen? In non-ideal characteristics, like this region remains same. Now in the mid voltage region, it should be nearly constant, but it will rise up a bit with respect to the voltage. Not much rise, but with respect to the voltage as well, it will rise. And then at a particular voltage, it will rise very fastly, like very high amount of current would flow. So basically there are three kind of region 1, region 2 and region 3. In region 1, the current remains nearly the same. Why it remains nearly the same? So let's see on the next page. So this is your non-ideal characteristics. Okay, I versus VA, I should write down I versus VA. So this is your non-ideal characteristics. Like in the low voltage region, it remains the same. In mid voltage region, it rises a bit with the applied voltage, and after that, at a particular voltage, which is known as breakdown voltage. At this breakdown voltage, what will happen? The current will rise up very fastly, like very high amount of current would flow. So in low voltage region, what is happening? Who will be our matter of concern now? The depletion region. In depletion region, previously at the equilibrium, our electron and hole concentration N into P was equals to Ni square. Under the reverse bias, N into P equals to Ni square e to the power Va by Vt. When you are applying very low voltage, at a very low voltage, the current is also less. Like what is your I total? Now, non-ideal current we are writing down. So it would be equals to I ideal for sure. This is already very less. Along with that, if Va is very low, let's just say Va is some 10 millivolt only. So what you would do, e to the power minus 10 millivolt divided by 25 millivolt. That means the carrier concentration from equilibrium is being disturbed in a very low amount. Like at the equilibrium, you are having N into P equals to Ni square. Since you have applied a very low reverse bias, this is not changing much. Are you able to understand this point? This particular thing is not changing much. Along with that, this current is also very low, and this carrier concentration is also not changing much. So that's why depletion region will not do anything. Depletion region is saying that my carrier concentration is not changing in much amount, so I will not generate any current, I will not do anything. So whatever the ideal current you are having, the same ideal current you will have here as well in the region 1. So in the region 1, in low voltage region, nothing is happening. Now in the mid voltage region, what will happen? Now the voltage is good enough. Let's just say voltage is minus 0.1 volt. Okay, Va is minus 0.1 volt. So now this value will be good enough, right? E to the power minus 0.1 divided by 0.025. So now the carrier concentration inside the depletion region has gone down drastically. So now depletion region will be triggered. Depletion region will say that previously I was having N into P equals to Ni square. Now you have decreased my carrier concentration. If you have decreased the carrier concentration, I will oppose it. So previously I was having 2 holes. Now I am having only 1 hole. So what do you think what depletion region will do? It will generate the holes, right? What it needs to do? To maintain the equilibrium, the depletion region will start generating the holes. So in the mid voltage region, who will come into action? Generation current will come into action. Is that understandable to you? Because in the mid voltage region, the carrier concentration has gone drastically down, and because of that, depletion region will try to oppose it from the equilibrium, and it will generate some electron and holes. Why it is generating some electron and holes? Because the carrier concentration is going down. In the forward bias, what was happening? The carrier concentration was increasing. Previously I was having 2, but in forward bias it became 4. So since it became 4, now the depletion region will kill these 2 holes. That means it will recombine these 2 holes. So in the forward bias, recombination current was coming into action. In the reverse bias, generation current would come into action. Is that understandable to you or not? But this generation current in forward bias, the recombination current was effective in the low voltage region, right? In forward bias, recombination current was effective in the low voltage region. Why not in the high voltage region? Because in high voltage region, this ideal current was increasing very drastically in case of forward bias. But in case of reverse bias, what is happening? This current is very low. Here, this particular current is very low. In mid voltage region, this particular current is I not only, which is very low only, right? Not very high. But since this is changing very drastically, generation current would come into action. And now this generation current would say that now I will increase. You are already very low, I don't care, but at least I will increase now. And if I am increasing, that means there will be a slope. Previously you were nearly constant only. You are very low, I don't care about it. But now you guys are disturbing my equilibrium carrier concentration condition. So because of that, I will have to generate some generation current, and that current will increase with respect to the applied voltage. So that's why I have seen some linear kind of increase, although this is not very large, but surely there is some linear kind of increase. So in this particular region, ideally you expected that I not constant current I would be getting, but no, with respect to the applied voltage, some current is increasing. Is that understandable to you? So region 1 and region 2 is clear to you, and how it is different from the forward bias, that is also clear to you. In forward bias, in low voltage region, in forward bias, this kind of characteristics we got, right? If I make it better, so this kind of characteristics we were getting in forward bias. So in forward bias, here your recombination current was effective. Why recombination current was not effective in this region? Because in this region, the ideal current has risen up very drastically. So if this has risen up very drastically, then this recombination current was not even coming into action. But here, ideal current was also not high. Along with that, recombination current was something good. So here we gave importance to the recombination current because it was comparable to the ideal current. But in this particular region, it was nowhere comparable to the ideal current. So we did not give any kind of importance to the recombination current. So ideal behavior we were having. Here what was the scenario? That sir, in low voltage region, even ideal current is very low. Along with that, carrier concentration is also not changing. So already current is very low. But even in the high voltage region, our ideal current is still very low. Our ideal current is still very low. But as I have applied very high voltage, the carrier concentration has gone down drastically. And because of this drastic decrease in the carrier concentration, the depletion width will get triggered and it will start generating electron and hole pairs. Because of that, some generation current would come into action, and that generation current would have some importance. So when you are adding up ideal current plus generation current, so this current has become dominating. Because of that, we are seeing a linear growth in the current. I hope everything is crystal clear to you without a single formula. Now what will happen in the third region? That is our matter of concern. So this is the most important part, that is the third region. So till this date in the examination, they never asked about these two regions, but they have surely discussed about this third region. Okay, so now this third region becomes important. So I total is already written there, I don't need to write it down. Now as you keep on increasing the reverse bias, so this electric field will become stronger and stronger. Because of this very high electric field, something would happen and the current would rise very fastly. So two kind of phenomena can take place. One is Jenner, other one is avalanche. Okay, two kind of phenomena can take place at this particular voltage. Okay, at this particular voltage, two kind of phenomena can take place, Jenner or avalanche. So we need to discuss both of the phenomena. We will discuss both of the phenomena. We will talk like what is actually happening inside the depletion region at a very high reverse bias voltage. So we will talk everything about it. But let's see the theory of region 1 and region 2. So we have written down a brief theory for region 1 and region 2. So low reverse bias at very small reverse bias voltage, the electric field is very weak and generation in the depletion region is negligible. The small current flowing is mainly due to the drift of minority carriers only, electrons in the p side and holes in the n side, right? So minute amount of current was flowing, equilibrium carrier concentration was also not changing much, that's why it remains the same. Okay, at moderate reverse bias voltage, as the reverse bias increases, the electric field will become stronger and depletion width will be widens. Now electron and hole pair inside the depletion region are swept across the field, producing a generation current. Or better theory could have been the electron and hole concentration inside the depletion region is actually going pretty down. Because of that, the depletion region will start generating some electron and holes. Because of that, the current would increase. So generation current would come into action. This theory is not written in that good manner, so this line should have been changed. So in a rough way, you can write down the line. What is the line? The line says that inside the depletion region at a very high reverse bias voltage, the carrier concentration has gone down. Since the carrier concentration has gone drastically down, the depletion width will try to oppose it because of the equilibrium condition. It will try to maintain its equilibrium condition. And since it is trying to maintain its equilibrium condition, it will start generating electron and hole pairs. Because of that, generation current would come into action. Although the current is nearly constant, the I naught current that is nearly constant, but generation current will be increasing with respect to the applied reverse bias. If you keep on increasing the reverse bias, carrier concentration will keep on going down and the generation current will keep on increasing. Because of that, you would see there is some slope in the mid voltage region. So this you can write down here. In brief manner only this has been written. Okay, could have been written in a better theory. So you can write down whatever that I have repeated. Okay, so hence the total reverse current increases slightly due to the minority carrier drift and a generation current. Okay. Now in the very high reverse bias, this is known as breakdown region. So your device has broken down, right? Let's just say there is some person who is hurting you, and you have, like, you are listening to him, still you are listening to him or her. Okay. So, but there would be a point where you will break down, right? Like this is something that you can still bear. I am bearing him, and suddenly I will break down. Like this is the point where diode is saying enough. Don't keep on increasing the reverse bias across me. If you keep on increasing the reverse bias across me, what I was supposed to do? I was supposed to generate a very low current, but you have crossed the limit. Now what I will do? I will generate very high current. Okay, so that's why it is known as breakdown region. Just passing the time, nothing else. So this is your breakdown region. Okay, so at a very high reverse bias, the electric field across the depletion region becomes very strong. This strong field can cause breakdown of the junction, allowing a very large current to flow. This breakdown may occur because of two phenomena: Zener breakdown or avalanche breakdown. In this region, the current will rise abruptly. So what is Zener breakdown? What is avalanche breakdown? Why the current rises abruptly? Let's see that. But before that, let's do a very quick review. Very quick revision we are doing. So in the valence band, whatever the electrons that are found, they are bound electrons, right? And those electrons doesn't conduct the current. Just a quick revision we are doing. After that, we will move to Zener breakdown and avalanche breakdown. Doesn't conduct the current. But whatever the electrons are found, not electron and hole, only electron. Whatever the electrons are found in the conduction band, they are known as free electron and they conduct the current. Like basically, if this is the scenario and if I apply a voltage here, what will happen? These free electrons will start moving and they will conduct the current. So they have no importance in conducting the current, but they have the importance in conducting the current, right? This we have already seen in our basic semiconductor physics. Why it is important? When we study about Zener breakdown, it will become important. Okay. Now, for reverse bias, this is the depletion width. And you know that in reverse bias, depletion width will increase. Now, if I have applied a very strong reverse bias, at high reverse bias, can I put V built in plus VR nearly equals to VR only? So what will happen? This formula would become two epsilon by Q 1 upon Na plus 1 upon Nd into VR, right? Now, Zener breakdown and avalanche breakdown, they will happen at high reverse bias only. Like now our matter of concern would be high reverse bias only, like very high voltage we are applying. So now our matter of concern has become high reverse bias only. Now at the high reverse bias, if I increase the doping concentration, then what will happen? Depletion width will decrease. Although, sir, in the reverse bias, the depletion width will increase only. I know that. In the reverse bias, if I keep on increasing the reverse bias, depletion width will increase only. But that increased depletion width, I want to decrease. Like I want to have minimum highest depletion width. Are you able to understand this statement? Minimum highest depletion width. Like at a particular reverse bias, I will get a depletion width. Let's just say 2 micrometer depletion width I am getting at reverse bias of 6 volt. Now, if I want to decrease this depletion width, what I need to do? I will increase the doping concentration. If Na and D more, that means depletion width will be lesser, right? Like a lot of time people get confused. Here I would be saying that, sir, higher doping, lesser depletion width. But sir, we are talking about the reverse bias. In reverse bias, how you are saying lesser depletion width? I know that in reverse bias, depletion width will be widening up. Depletion width would be widens only, like, right? The depletion width will be wide in the reverse bias. But if I increase the doping concentration, then what can happen? The depletion width can decrease. So the highest depletion width, I want that to be minimum. So what does that mean? Here just I am putting up only one thing, that if I increase the doping, then what will happen? Depletion width I can decrease. Simple thing, straightforward. Okay, so let's go to our two phenomena, Zener and avalanche. Don't look here. First we are going to discuss about Zener breakdown. So what I have done, high reverse bias is there. Both will happen at high reverse bias. High reverse bias. So if high reverse bias is there, then this particular scenario, like this particular barrier, this would have increased, this barrier would have been V built in plus VR, or better I should write down Q V built in plus VR, right? You are having high barrier. Now in the valence band, you are having some bound electron. Now just tell me one thing, if these three bound electron wants to conduct the current, if these three electrons are saying that I need to conduct the current, then what should be their path? That first you go to conduction band, and once you have reached to the conduction band, and then you roll down here and conduct the current. Like once you are here, then it would be very easy for you, right? You will say to this electron that first you get enough energy, go to the conduction band, and once you have reached here, you know that there is very high slope, then there is very high chance that you will be able to conduct the current, because you will be rolling down here and you will be able to conduct the current. This is already a reverse bias, so minority carrier, this is your P side, right? This is my P side and this is your N side. So since you are in the reverse bias, so minority carrier concentration have very high chances of conducting the current, but first task is you go from here to here, then only you will be able to reach here. This is what you are saying to the electron. But what electron said? Electron said that I am in this energy level, I can see the conduction band of N side is having lesser energy level than me. This is one state, this is another state. One electron is here. So this electron can easily travel from here to here, no? So this electron will say that, sir, instead of going like this, what I would do? I would directly jump from here to here. Let me choose a different color of pen. This electron will say that I will directly jump from here to here. It's just that it needs to cross this depletion width. So this particular electron needs to cross this particular barrier, and it will directly jump from the conduction band of P side to the conduction band of, from the valence band of P side to the conduction band of N side. And once you are in the conduction band, you are able to conduct the current. So this particular process is known as tunneling. This electron tunnels through this electron is tunneling from the valence band of P side to the conduction band of N side directly, and because of that very high current would flow. Like a lot of electrons from here to here will directly tunneling through. Like there are a lot of bound electrons, no? And those bound electrons which were not able to conduct the current, first they need to get some energy, then they need to go to conduction band, and then they will conduct the current. But what really happened? Because the electric field was very high, that's why this barrier was very high. Since this barrier was very high, this guy has came very down. So the conduction band of N side has come very down, and this guy has went very up. So the energy level of valence band and the energy level of conduction band, they have become almost near. Then what bound electron of valence band can say? That I can directly tunnel from the P side of valence band to the N side of conduction band. Now sir, how this tunneling process takes place, that is not a matter of concern. You would be thinking that, sir, how it will be going from here to here? What is the meaning of crossing this barrier? You don't need to worry about that. If I start explaining, it would take more than 4 to 5 hours. Okay. So tunneling process is not specifically mentioned in your syllabus. If it was mentioned, we would have explained that, we would understand about tunnel diode as well. But it is not mentioned, only Jenner diode are mentioned. So because of that, I am just telling that what is the meaning of Jenner breakdown. Jenner breakdown simply means from the valence band, whatever the bound electron you were having on the P side, they have directly jumped to the N side conduction band. And since they are in the conduction band, now they will be able to conduct the current. Now what is the physical meaning? So physically what is happening? So physically what is happening is that, like, let's just say this was our PN junction. So although this diagram I have made for avalanche breakdown, but here I am explaining about Jenner breakdown only. So physical meaning is that this electric field has become so strong such that whatever the, let's just say in P side you were having some boron atom, you were having some hole, and 3 bound electrons were there, and then this was your silicon atom. So this was the scenario, silicon is there. So this was your scenario, right? Now this electric field has become so strong that this electric field itself is enough to break this bond. This electric field has become so strong that this electric field itself has become strong enough that it will break this bond. And since the bond is broken, electron has become free. And since the electron has become free, now it can travel. So electric field direction is on this. This electron has become free, so this electron will travel here. So this electron has directly went from p side to n side. This is the same scenario that is happening. So this is the physical scenario that I am explaining. And if you want to explain through the Venn diagram, then this is how you can explain through the Venn diagram. So this electric field is itself very strong enough such that it has broken this bond, and whatever the free electron is there, that is able to travel from the p side to n side. So why it is happening? It is happening because of the strong electric field. So that's why it is known as field ionization. What it is known as? Field ionization. Okay. All good. So this is about your Jenner breakdown. I hope you are able to understand. Now avalanche breakdown also feels like Jenner breakdown only, but there is a difference. Here what is the scenario? Here moderate doping is there, that means depletion width will be widen up. Like depletion width will be large enough. Here depletion width is very low, very narrow. But here depletion width will be large enough. Now what will happen? Here also there will be strong electric field. Although that electric field will not be as strong as this one, but still it will be strong only. Here whatever the electric field that you are having, that is very strong. But here the electric field is not very strong. Although it is strong but not very strong. Why this electric field is strong? Can anyone tell? Because depletion width is narrower, no? If depletion width is narrower, then the field will be stronger. Why is that so? Emax equals to, sorry, not Emax, V built in equals to half into base into Emax. Do you remember this diagram? This was W, this was your Emax. This is your maximum electric field if it goes here. So what you are getting? In place of V built in, this time we will write down V built in plus VR, right? Because the total bias in the depletion width has become V built in plus VR. V built in plus VR divided by 2, sorry, V built in plus VR divided by W into 2. That has become your Emax. So if this is less, if depletion width is less, then electric field would be more. So if depletion width is less, more doping, less depletion width, more electric field. So electric field would be more, right? So this electric field is more. So here there is more electric field. Here also there is high electric field, but it is not as strong as this particular electric field. So now what will happen? Now in this electric field, some electrons will be there. Minority electrons would be there. I should make it here. Now this minority electron will get good enough energy. Like high reverse bias is there, high electric field is there. Although this electric field is not comparable to this one, but still it is very high. Since we are applying very high electric field, then this electron will move at a good speed. Like this electron will get good enough energy. Now this particular electron is getting good enough energy. Now inside the depletion region, let's go to where it will move. In this direction it will move. So let's go to this scenario. Here what we are having? Here we are having, let's talk here only. In the p side what we are having boron atom. Now boron atom, this kind of boron atom we are having. Now this electron is having very high energy. So what this electron would do? This electron will simply knock out this particular electron. What this electron is doing? This electron was traveling, it has knocked out this particular electron. So since it has knocked out this particular electron, then what will happen? Here hole will become and the electron has knocked out. Now this is also free. Now this has also become free. So from one boron atom you are getting 2 free electrons. Then what will be the scenario? Again the same scenario. Now these 2 free guys, what they will do? They will knock out this guy. They will knock out this guy. From here you will get 2 more electrons, right? From here you will get 2 more electrons. Now these 2 more electrons and these 2 more electrons are already there. So total has become 4 electrons. Now these 4 electrons will knock out more. 4 electrons will knock out more 4, 8. Then 8 will knock out more 8, 16. 16 will knock out more 16, 32. So now what will happen? A lot of electron and hole pairs will be generated, and because of that current will rise up very fastly. A lot of current would flow. So because of the stronger electric field, the electron gain enough energy and that enough energy is knocking out the other bound electrons. These are your bound electrons, not free electrons. Whatever the free electrons were there, they were already conducting the current. They were already conducting this much of current. But now at higher electric field, what is happening? The bound electrons are broken. Now what is the difference between Jenner and avalanche? In Jenner breakdown, the electric field was so strong, that from the electric field only, this bound electron was traveling to the conduction band. But here, electric field is decent enough strong. This electric field is giving enough energy to this particular electron. And now this electron is knocking out these particular electrons. So, in Jenner breakdown, who is responsible for the breaking of covalent bond? Field is responsible. Let me repeat. In Jenner breakdown, who is responsible for the breaking of covalent bond? Here as well covalent bonds were broken. Here as well covalent bonds are broken. But in Jenner breakdown, electric field was responsible for this. In avalanche breakdown, electric field will give enough energy to the electron, and now electron are responsible for breaking those covalent bond. This is the difference. So this is known as impact ionization. That means because of the impact between electron and electron, more electron and hole pair are being generated. So this is known as impact ionization. Is that clear to you or not? Okay, it is complete theory only, but this is how I can explain the theory. There is no other way. Okay, I cannot explain it with respect to the formula. The theory has to be explained in this manner only. The best possible thing, as much points as I can tell, that I have told here. Is that clear? Or shall I repeat it again? So let's repeat it one more time in a quicker manner. I will repeat Jenner breakdown and avalanche breakdown. Starting with the avalanche breakdown, you are having decent enough electric field. Now that decent enough electric field is good enough to give enough energy to the electron. These electrons will knock out the other bound electrons present in p side and n side. Because of that, a lot of electron and hole pair will be generated, and they will be conducting a very high amount of current. In Jenner breakdown, the field is very, very strong, and that strong electric field is enough to break the covalent bond of p side, covalent bond of p side or n side also you can say. So this electric field is enough to break the covalent bond. That's why the electrons are directly traveling from the valence band to the conduction band, and that's why electron hole pairs are being generated and the current is flowing. So here field ionization, there impact ionization. I hope that is clear to you. Complete theory has been written. Another phenomena is there. That phenomena is about temperature. Okay. So here if the temperature rises, the breakdown voltage will decrease. Like first thing is, who will need more electric field? Here Emax is more. Emax is more. Here W depletion is less. Here Emax is still good enough, but not more than this. So Emax less, but W depletion is more. Why do we require more depletion width here? Because electron needs the path to travel, no? Like electron would require the path to travel. Electron would say that I need to, like here electrons need to travel. First they will get the energy. Then they will travel. Then two more electrons will travel. Then two more electrons will travel. So in that manner, electrons need to travel here. So they need some path, right? So that's why here the width is wider. Okay, width is more here. Depletion width is more. Emax is lesser. Now, which will occur first? Jenner breakdown will occur first, or avalanche breakdown would occur first? So on the first glance, it may look like that, sir, Emax is more. That means the Jenner breakdown voltage should be more. Like what we know, electric field is proportional to voltage. That means this would require higher voltage and this would require lesser voltage. No. Two phenomena are there, no? Depletion width is also less, no? So this occur first. Jenner breakdown would be occurring first and avalanche breakdown would be occurring later on. So first actually Jenner breakdown occurs. Jenner breakdown would be occurring at a lower voltage. Okay, like this depletion width is so much narrow that even the lower voltage would give it more than enough electric field. Are you able to understand this point? So you can either remember it or like you cannot actually understand it. There is nothing to understand. Like here you would require more electric field, here you would require less electric field, here depletion width would be more, here depletion width would be less. Now all come down to the voltage. So what is the formula of voltage we write down? V built in plus VR. that would be half W E max. Now this guy is more, this guy is less. Here opposite thing is there, that this guy is less, this guy is more. So for whom VR would be higher? You cannot actually understand by the formula. So you can say that it is observed that this in Jenner breakdown is occurring at a lower voltage than the avalanche breakdown. But Jenner breakdown will occur in those kind of PN junction where there is high doping. Relatively there is higher doping. Okay, and if there is higher doping, that means lesser depletion width would be there. And avalanche breakdown would be occurring in those kind of diodes where there is moderate doping and moderate depletion width. Both would require higher voltage, both would require higher electric field, but here I would require more electric field. Because of the more electric field, that electric field is so strong that this electric field is itself breaking the bond. The electric field is itself breaking the covalent bond, and because of that electron hole pairs are generated and the current is rising. But here electric field is strong, but that electric field is first giving energy to the bound electrons. Sorry, not bound electrons. First this electric field is giving energy to these free electrons, and now these free electrons are breaking the covalent bond of other atoms, and because of that electron hole pairs are being generated, and now those electrons are breaking other covalent bond. More electron hole pairs are being generated. Those more electrons will break more covalent bond, and a lot of current would rise up. Okay, is that clear? Now question would come down to who would require less breakdown voltage, who would require high breakdown voltage. So from this particular formula we cannot understand. So you can say physically it is found that Jenner breakdown would be occurring at lower breakdown voltage and avalanche breakdown would be occurring at higher breakdown voltage. How you can tell it? That here depletion width will be very less. Since depletion width is very less, the electric field is actually very high, and so much of high electric field is there that even if I apply very low voltage, then also I would be able to get the breakdown voltage. Actually breakdown voltage would occur nearly around 4 to 6 volt, but avalanche breakdown would occur nearly around 6 to 8 volt. Okay, this is the reverse bias I am telling. So someone can say -4, -6, -6, -8. Okay, so at the reverse bias of 4 to 6 volt, Jenner breakdown would occur, and then avalanche breakdown would occur. You can simply remember it. Okay, so there is no particular explanation for this. At lesser voltage, Jenner breakdown would occur, and at higher voltage, avalanche breakdown would occur. The difference is that this kind of breakdown would be occurring in relatively higher doping, and this kind of breakdown would be occurring in relatively lower doping. If lower doping is there, that means moderate depletion width is there. So electron will get enough space to move on. But here electron doesn't want any space to move on. What they want, they directly want to jump from the valence band to the conduction band. This is what they want. Okay, so this is your Jenner breakdown, this is your avalanche breakdown. I hope I have given more than enough theory. And yeah, one more thing was there. Here I am saying VZ is less, or V breakdown is less. Here V breakdown is more. Temperature dependence. So this is negative temperature coefficient. What does that mean? Jenner breakdown voltage is negative temperature coefficient. That means as the temperature rises, the Jenner breakdown voltage decreases. Why so? You have understood one thing, that if you have kept your semiconductor at 0 Kelvin, then what will happen? At 0 Kelvin, no electrons from the valence band will go to the conduction band. But as you increase the temperature, what happens? The electrons can travel from the valence band to the conduction band. That means some covalent bond get broken. So at higher temperature, the covalent bonds become weaker, right? If temperature is high, the covalent bonds become weaker, right? Now already very high electric field is there. Covalent bond has become weaker only. That means this particular electric field would be able to break more bonds. Are you able to understand this point? At higher temperature, the bond would become weaker, no? Right? So if the bond has become weaker, then what will happen? This electric field would be able to break more bonds and more current would flow. So previously, if I required an electric field of, let's just say, 10 volt per centimeter, now I would require lesser electric field. If previously I required this much of electric field to break the bond, but now the bond has become weaker, that means I would require lesser electric field. And if I am requiring lesser electric field, what does that mean? That means I will require lesser voltage. So my Vz would decrease, my breakdown voltage would decrease. Is that understandable to you? As the temperature increases, the covalent bond becomes less stronger. Previously, I was requiring a certain electric field to break the bond. Now I would require less electric field to break the bond. That means my breakdown would occur at a lesser voltage only. Previously, my breakdown was occurring at 5 volt. Now the breakdown would occur at 4 volt only. That means the breakdown voltage has decreased with the increase in temperature. Is that clear to you? So this is about Jenner breakdown. I hope that you have understood. Let's repeat it once more. So as the temperature increases, the covalent bond becomes weaker. Now lesser electric field is enough to break those covalent bond. That means I would require a less electric field. That means I would require a less reverse bias voltage at which the breakdown would occur. So if the reverse bias voltage to get the required breakdown that has decreased, that means my Jenner breakdown voltage has decreased. So it is your negative temperature coefficient. So with respect to the increase in temperature, my breakdown voltage is decreasing. First one. What about the avalanche breakdown? So in the avalanche breakdown, this covalent bond breaking is not important. What is important? The electrons should knock out the electron. This is important. Like basically, let's just say there is one electron and this is your free electron, this is your bound electron. This is your bound electron and this is your free electron. So in avalanche breakdown, what is important? The important part is that this electron should strike this electron. That's it. Like this bond is not important. Important is that impactful striking should be there or impactful ionization should be there. Are you able to understand this point? Like if this electron strikes here, then this electron will not be able to knock it off. Like if you want to knock off your opponent, that means you need to go head to head. Then only you will be able to knock it off. If you are punching on stomach or if you are punching on head, sorry, not head. If you are punching on hands or if you are punching on stomach, then you will not be able to knock it off. But if you are directly punching on head, then you will be able to knock it off. So here what is my matter of concern? That this free electron should knock this electron out. But as the temperature increases, what will happen? The atoms will start vibrating. Like atoms are vibrating. Let's just say initially atoms are not vibrating. So what is the target of this electron? That I will directly knock it off. But now what is the scenario? They are vibrating. They are vibrating. Along with that, their covalent bond are also vibrating. So now it will be tougher for this electron to knock it off. No? Are you able to understand this point? Previously, one guy was standing still. If some guy is standing there and you need to knock him off, you will directly punch him. But now this guy is moving. So now it will be tougher for you to knock him off. Are you able to understand this point? Like this guy is moving, you put a punch, his head was here, so you will not be able to punch him. Then you again put a punch, his head was on the other side. Again you are not able to punch him, right? So if they are moving, if atoms start vibrating, then it will be tougher for you to knock them off, right? So that's why at higher temperature, the avalanche breakdown voltage will increase. That means now I would require a higher electric field. Are you able to understand this point? Right? Look, these reasoning are not that important, but in one-liner questions can be framed. Which of the following statements are true? Option 1. At higher temperature, you would require lesser breakdown voltage in case of Jenner breakdown. Option 2. At higher temperature, you would require more breakdown voltage in case of avalanche breakdown. Option 3, opposite of that. Which of the 4 following statements are true? Directly this kind of question can come, and they have actually come as well. So surely these kind of questions can come in your examination. So that's why you need to remember those points. You will not have to worry much about that because all the theory has been written. So you just need to revise the slides, nothing else. But here I have explained everything. Right? Starting with Jenner, free electrons will be moving here directly. Sorry, bound electrons will be directly moving. Electric field is so strong. Here there is no impact ionization. Electron and electron are not like electron and electrons are not knocking each them off, right? They are not knocking each other off. What they are doing? Electric field is so strong that it is breaking the covalent bond, electron hole pairs are being generated. So this is your Jenner breakdown. It is occurring at a higher electric field, lesser depletion width and lesser breakdown voltage. Avalanche breakdown, electric field is decent enough strong. It will give enough energy to the electron. This electron will make a impactful collision with the other electron, and that electron will be knocked off. Because of that, 2 electrons are generated. Those 2 electrons will knock off other 2 electrons. Those 4 electrons will knock off other 4 electrons. In that manner, a lot of electron hole pair will be generated and current would rise up. So here electric field should be strong enough, but it is not as strong as Jenner breakdown. Okay, because here there are actually two phenomena. Strong electric field has given energy to the electron, and that electron is knocking off the other electron. And in the Jenner breakdown, what is happening? Electric field itself is very strong enough that from the bound electric field is itself very strong enough that the covalent bond is broken and electron hole pairs are generated. Okay. And what about the temperature? So as the temperature rises, the covalent bond becomes weaker, and if the covalent bonds are weaker, then you would require less voltage to break the bond. That means at a higher temperature, the breakdown voltage in case of Jenner breakdown would go down, but in case of avalanche breakdown, the lattice scattering would increase. So electron wanted to strike to these bound electron, but what may happen is that sometimes they will be striking to the atom. Like basically they are moving, no? At higher temperature, scattering is more. So they are moving, right? Your atom is also moving, these bonds are also moving. So electron wanted to strike to this electron, but actually what really happened? It actually struck this atom. So there was no impactful collision. So impactful collision has gone down. That means you need to apply higher electric field now. That means you need to apply higher voltage. Okay. So at higher temperature, the breakdown voltage in case of avalanche breakdown will increase. So this is the complete theory that has been written for Jenner breakdown. It is known as tunneling breakdown as well. Why tunneling breakdown? Because electrons are tunneling through that depletion width from valence band of p side to the conduction band of n side. So this is known as tunneling breakdown as well. So this theory has been written. General breakdown occurs in heavily doped diodes where the depletion region is very narrow and the electric field is extremely strong at a low reverse bias voltage. Because of this high electric field, the energy bands will be bending very sharply, and the valence band of p side comes very close to the conduction band of n side. In this condition, the electron can directly tunnel from the valence band of p side to the conduction band of n side without any collision. The tunneling of electron causes a sudden flow of current at a comparatively low breakdown voltage. Thus, Jenner breakdown is a quantum mechanical tunneling process. It is a tunneling process. What is the meaning of quantum mechanical? That you don't need to understand, because quantum physics is not in your syllabus, right? So it is a quantum mechanical tunneling process that will dominate in highly doped and low voltage diode. High doped, lesser depletion width and lesser breakdown voltage. Temperature dependence. The Jenner breakdown voltage decreases with increase in temperature. It has negative temperature coefficient. This happens because as the temperature increases, more electrons are thermally excited, making it easier for them to tunnel from valence band to the conduction band. Or it is the same thing, only the covalent bond is becoming weaker. Since the covalent bond is becoming weaker, then more of the electrons will be thermally excited. They will be moving from the valence band of p side to the conduction band of n side. So this is the same thing that has been written. As a result, less electric field is required to initiate the tunneling. That's why the Jenner breakdown voltage would decrease with respect to the temperature. And what about the avalanche breakdown? So all these statements have been written for avalanche breakdown as well. Let's read it out. It would occur in lightly doped diodes where depletion region is wide and the electric field is moderate. Okay, moderate enough electric field is there. Under the high reverse bias, the electric field will give large kinetic energy to free electrons present in the depletion region. These energetic electrons will collide with the atom, knocking out the additional electrons from their bonds and generating new electron hole pair. These newly free carriers are also accelerated, leading to a chain reaction called impact ionization. So in that manner, a lot of electron hole pairs will be generated. This rapid process will increase the number of free carriers, causing a sudden and a large increase in the reverse current. So thus, avalanche breakdown is a collision based process that dominates in lightly doped and high voltage diode. Light doping, that means higher depletion width and higher reverse bias voltage. Okay, so temperature dependence of avalanche breakdown voltage. The avalanche breakdown voltage increases with temperature increase. Okay, if the temperature increases, the avalanche breakdown voltage will increase, because at the higher temperature, carrier collide more often with the atom and get less energy from the electric field. So to get them the required energy, what will happen? We need to apply more electric field. Okay, thus more electric field means larger voltage needs to be applied to get the same kind of breakdown. Okay, so as the temperature increases, the avalanche breakdown voltage increases only. Okay, so a larger voltage is needed to start the breakdown. This is the difference between Jenner and avalanche breakdown. All the difference has been written and all the difference has been explained as well. So all these are the difference. Basic mechanism, you can read it. Doping level, general breakdown would require high doping, this would require lesser doping. Depletion width, lesser depletion width, more depletion width. Required electric field, very high electric field, less electric field. It would occur at lesser voltage, it would occur at more voltage. Temperature dependence, just now I explained it. Energy band explanation also I have given. So from this slide only, if any theoretical question will be framed, from this slide only it will be framed. Everything is written here. Okay, so this slide is your matter of concern, nothing else. So you can simply read it. When you revise this particular topic, how would you revise it? Within 5 minutes you will be able to revise. First you will see this particular thing, that here this particular scenario is there, why this thing is there, electron from the valence band will move to the conduction band, here electron will get enough energy, it will knock out. Then you would read this theory in a very quick manner, you would read this theory in a very quick manner, and then you will compare. That's it. So theoretical question can be framed from here in this manner. Sir, what kind of numerical question can be framed? So this kind of numerical question can be framed. Only one numerical question can be framed, which is this one. Only one kind of numerical problem. Otherwise, from this particular topic, we started from here. From where we started? Non-ideal characteristics. From here, what can be framed? They can only ask what kind of current would be there, generation or recombination, and where the current would be dominating. The current would be dominating in mid reverse bias voltage. The current would be generation current, not the recombination current. So this question they can ask. Then at very high forward bias voltage, they can talk about Jenner breakdown and avalanche breakdown. This is the theory of Jenner, this is the theory of avalanche, this is the difference. So these theoretical questions they can ask, and from if they want to ask any numerical problem, then this is the numerical problem they can ask. You can directly do it, very easily you can do it. So try solving this problem on your own. What is given? Assume that P plus N silicon Jenner diode is fabricated, given doping concentration is there, and the Na is given. Relative permittivity is given. Critical electric field for the Jenner diode. What is critical electric field? It is the maximum electric field at which the Jenner breakdown is occurring. So what is critical electric field? This is the electric field at which Jenner breakdown is occurring. So electric field is given, charge value is given, you need to find out the breakdown voltage. So basically you need to find out the reverse bias that has been applied. That's it. This is something that you need to find out. Now you know that the breakdown voltage, you write down VBR, that would be much greater than V built in, no? Although in this question I can find out the V built in, but I will ignore it. V built in will be nearly 0, I will take. You can find out V built in here, that would be nothing compared to V breakdown. Okay. Oh, let's not ignore it, we will take it into action. In the examination as well, never ever ignore built-in potential. If you are able to find out, like here Na value is given, Nd value is given, so I guess you will be able to find out the built-in potential. Ni value is given. Okay, Ni value is not given. So now I will ignore it. Nowhere Ni value is mentioned. No? So now I will ignore my built-in potential. Okay, this will be ignored now. To find out the built-in potential, what you will require? Kt ln Na Nd by Ni square. So if they are not giving you Ni value, that means they want you to ignore the value of V built-in. That means you will consider that your breakdown voltage is much larger than V built in. So what is given? Electric field is given. What is that? What is the formula of electric field? Sir, Q N D Xn divided by epsilon, or Q Na Xp divided by epsilon. Smart assumption. Let's make smart assumption, because what I can see, Nd Na ratio. Nd ratio Na. What is that? Sir, 25 times, right? 10 to the power 7, 10 to the power 18, sorry, 10 to the power 17, 10 to the power 18. So 10 times 2.5. So 25 ratio is there, 1 ratio 25. What does that mean? Xn ratio Xp would be 25 ratio 1. And this we have again and again proved that W depletion would be nearly equals to Xn now. Right? And what will be the formula of Xn, or you can call it W depletion? So that formula would become 2 epsilon by Q, 1 upon Na, that would be ignored because Na is very large, that means 1 upon Na would be very less, so that would be ignored. And here V built in plus V breakdown we used to write down, V built in we cannot find out, so directly I will write down V breakdown. Is that understandable to you how this formula came? Yes sir, we have seen enough numerical, now I am comfortable with this particular formula. So what I got? Critical electric field is Q Nd divided by epsilon. In place of Xn, what I can put? This formula, 2 epsilon divided by Q Nd, and V breakdown. So you don't need to mug it up. You already remember the other formula. From there you will be able to derive it very easily, right? So you can see that so Q critical is coming out to be under root 2 Q and D divided by epsilon V breakdown. Yeah. So V breakdown we need to find out. So from here our V breakdown would come out to be epsilon into E critical square divided by 2Q and D. So this is your breakdown formula. A lot of people directly remember it, but you are not going to remember it. You will be able to derive it in the examination hall. Okay. So V breakdown we are getting as epsilon. Now I can write down the value 11.7 into 8.85 into 10 to the power minus 14. E critical. So 36 into 10 to the power 10. Right. 36 into 10 to the power 10. 2Q and D. 2 into 1.6 into 10 to the power minus 19 into ND. 2 into 10 to the power 17. So this is your breakdown voltage. 10 to the power minus 4 it would be there. This will be 10 to the power minus 2. That would become 10 to the power minus 2. Into 8.85 into 36 divided by 2 divided by 2 divided by 1.6. 5.82. So breakdown voltage is coming out to be 5.82 volt. Okay, so this is the answer. So in this manner you can find out the breakdown voltage. So whatever the kind of questions can be asked, that has been discussed here. Theoretical, numerical. Okay, and from here only one kind of question can be asked, that what kind of generation current would be there. It would be depending on the voltage. Okay, and it will be generation or recombination. It would be generation. So that's it. This particular topic we have discussed. So mostly whatever that we wanted to discuss in our reverse bias, that has been completed. Starting with the basic physical meaning, energy band diagram. Then in between suddenly we move towards some numerical problem of depletion width. Then we studied about again suddenly we studied about some capacitors. Then depletion capacitance we saw, or transition capacitance you can call it, and diffusion capacitance we saw. And then we move to our current equation. Ideally we should have moved to the current equation initially only, but it is not that important. Important parts were your junction capacitance, depletion capacitance, or transition capacitance, or diffusion capacitance, whatever you call that. Along with that, those W depletion numerical problem as well. Although they are very simple topic, but a lot of questions are asked from those particular topic. That's why we saw it earlier, and then we talked about the current equation. Current equation is also important, but the other part was very important actually. Okay, so these questions we have seen. Now we need to study a topic which is known as transients in PN junction diode. What is the meaning of transient? Transient means that how it would depend with respect to the time. So I need to draw the current versus time plot. So what I have given, I have initially given a forward bias, then I will change it to the reverse bias. So in forward bias, very high amount of current should flow. In reverse bias, zero current would flow. So I want to check like here I was having forward bias, that means some good amount of current was flowing. Just as I make the reverse bias, zero current should flow, like nearly very less current should flow. But is it happening or something else is happening? That I need to check. Okay. So what I am going to check, current versus time plot I need to make. So previously good amount of current was there. Just as I change the bias, the current should be negative and very low. But is it happening or something else is happening? So this particular plot I need to check. Okay. So this is known as transients on PN junction diode. But before that, there is a prerequisite that we will discuss. But let's see whether we discuss in this video or shall I make another video. So I will see the length of this video and then I will take a call that whether I should make a separate video or shall we discuss in this particular video only. Okay. So yeah, you also drink some water. I will also drink some water and then I will come back. Yeah, welcome back guys. So now we will see the transient analysis on PN junction diode. Okay. But before that, let's see an important note that how do you replace PN junction diode in circuit analysis. Okay. So this side is our P, this side is our N. Let's just say this node is A and this node is B. So node A will be replaced by this kind of structure and node B will be replaced by this kind of structure. Basically, this side is P, this side is N. Okay. So on the side where you can see the triangle, that side is P and this vertical line where you see that side is N. Okay. So this is P and N. This is your node A, this is your node B. So this is how you replace your PN junction in circuit analysis. If you have studied analog electronics, then you would have seen this particular circuitry a lot of time, right? This is your PN junction, this kind of diode you are having. Now when it is forward biased, what is the meaning of forward bias? That this kind of biasing you are doing. Like P is connected with positive and N is connected with negative. So when it is forward biased, then you replace your diode. Let's just say it is forward biased. Okay. So when it is forward biased, so it will be replaced by its cut-in voltage. Let's just say cut-in voltage is 0.6. So it will be replaced by a battery of 0.6 volt. Positive side with P, positive side with the positive terminal of battery, negative side with negative terminal of battery. So it will be replaced with the battery of 0.6 volt in forward bias. Or if cut-in voltage is not mentioned, then it will be simply replaced with short circuit. Like cut-in voltage is 0. If I consider cut-in voltage is 0, if this is 0 volt means short circuit only. So this is how you replace the diode in circuit analysis. In circuit analysis, diode will be replaced with a simple battery and that battery will be your cut-in voltage. P side will be positive, N side will be negative. And if cut-in voltage is not mentioned, it will be simply a short circuit path. And in the reverse bias, diode will be replaced with, this is your reverse bias. What is the meaning of reverse bias? N is connected with positive and P is connected with negative. So if it is reverse bias, then diode will be simply open circuit. Okay. Diode will be nothing but open circuited. So this is about the circuit analysis. We are going to use it somewhere. That's why we are studying it. What we are studying? PN junction is there. This is how you will be representing it. If it is forward biased, then it will be simply replaced by a battery or short circuit. If it is reverse biased, then it will be replaced by open circuit. Okay. So let's understand the scenario of transients on PN junction diode. So what is our setup? This is our PN junction. P side is connected with positive and N side is connected with negative for t less than 0. Okay. Switch is at S1 for a very long time. That means for t less than 0, it was always at S1. So this particular part was not there. For t less than 0, this particular part was not even there. But for t greater than 0, what happened? For t greater than 0, this switch got moved from here to here. Basically, what was your circuitry for t less than 0? For t less than 0, this was the circuitry. There was this RF connected. Then there was this VF connected. VF, RF, and then there was this PN junction was connected. So can I replace it with diode? Yes, sir. Now, this is your P side, this is your N side. So this was your condition for t less than 0. Here you can see that diode is forward biased. P is connected with positive, N will be connected with negative. So what you can see? You can see that diode is forward biased. If it is forward biased, then what you can do? Sir, simply my diode will be replaced with a simple battery. So this PN diode it will simply become a battery. That's it. So if it is forward biased, diode can be replaced with a simple battery. So this will become your VF, this will become your RF. Now if I ask what is the current that is flowing through the diode? The current that is flowing through the diode is I. So the current that is flowing through the diode, that is I. So can I say my I is equals to VF by RF? Very simple circuit analysis you can do. Voltage divided by the resistance, VF by RF. So can I call it IF only? Yes, sir. So for t less than 0, the diode was forward biased. Now if the diode is forward biased, it will be replaced with the short circuit path. That means the current that is flowing is VF by RF. It would be replaced with its cut-in voltage, but cut-in voltage is not given. I am taking cut-in voltage is 0 only. So it will be replaced with a short circuit. So this kind of current I am getting, and I am calling that current as IF. So this is the scenario for t less than 0. So what you have understood, for t less than 0, the current is this much. Ignore this diagram as of now. Just understand that this is my current IF for t less than 0. Okay. Now, if it was forward bias, then inside the PN junction, what would have happened? If it is forward bias, then what would have happened? Holes from P side would have gone to N side, and electrons from N side would have gone to the P side. That means holes and electrons would have been injected from P side and N side. Right? That means minority excess carrier concentration have been injected. So here the concentration of here the concentration of hole has increased. Like concentration of holes on N side at x equals to xn, and this is my xp. So here concentration of electron on P side at x equals to minus xp. Along with that, inside the depletion region as well, the excess carrier concentration has increased. So basically carrier concentration has increased both on P side and N side. Now what you are doing the reverse bias. In reverse bias, what is the condition? How does the plot look like? So depletion width would be widened up. Along with that, the plot will be looking somewhat like this. The plot will be looking somewhat like this. So forget about the depletion region. I know that depletion region will be widened up, but as of now we are not caring about the depletion region. I just know that this is my reverse bias condition. This is my forward bias condition. In reverse bias, what will be the condition I will be achieving? Sir, this kind of condition you will be achieving in the reverse bias. So this is your reverse bias condition. And if this condition is achieved, I know that in reverse bias current will be negative but very low. The current will be minus I naught. Now the important part is, just as you change the switch at t greater than 0, at t equals to 0 plus, what is the condition? At t equals to 0 plus. At t equals to 0 plus, what you have done? This particular part is gone. Now this particular part has come into action. That means at t equals to 0 plus, the condition is, this is your PN junction diode, right? Now it is connected to RR and VR. But notice the polarity. Now this has become the polarity. Okay. This is your P, this is your N. Now the question is, I know that my current will be minus I naught, but will this minus I naught current we get instantaneously? No. Because at t equals to 0, at t equals to 0 plus, what is the condition? At t equals to 0 plus, the condition is that this much excess carrier concentration we are having. Now I know that eventually this carrier concentration will go down to this concentration. But it will take some time, no? Right? You know that concentration will go from here to here. As of now, this is the concentration we are having. Eventually it will reach here. But it will take some time. Let's just say this was the condition at t equals to 0 minus. Now after that, after some time, what will happen? This condition we will achieve. Let's use different color of pen. We will achieve this condition. Like carrier concentration will go down now. Why carrier concentration will go down? Because here a lot of holes you are having, here you are having a lot of electrons. What I mean to say is that here I am having a lot of excess holes and here I am having a lot of excess electrons. Now what has happened? Arey yaar, this battery I made wrong. This is reverse bias, no? So this will be a reverse bias battery, VR. Now what has happened? This positive terminal has reached here. This negative terminal has reached here. That means external bias we have applied in this direction now. External bias we have applied in this direction. So now what this bias will do? This bias will say that whatever the excess holes are there, go back. Whatever the excess electrons are there, go back. That means now the bias, now this reverse bias is making sure that whatever the excess holes are there, they move back to their own direction and these excess electrons move back to their own direction. But it will take some time. It will not reach immediately. So at t equals to 0 plus, what will be the condition? At t equals to 0 plus, only minute amount of concentration would have gone down. Basically, at t equals to 0 plus, from here you would have come here only. Then after some time, from here you would come here. After some time, from here you would come here. Then after some time, you would reach the steady state condition. Now, until, not steady state condition, I should say, after some time you will reach the equilibrium condition. So until you reach the equilibrium condition, what is the equilibrium condition? This is your concentration of holes on N side at equilibrium. So until you reach the equilibrium, till that point, what diode will feel? Diode will feel that on N side I am having excess holes and on P side I am having excess electrons. This is what diode will feel until you reach to the thermal equilibrium condition. So this thermal equilibrium condition will take some time. Let's just say this time is at T equals to T1, this is the condition we are able to achieve. At T equals to T2, this is the condition we are able to achieve. At T equals to T3, this is the condition we are able to achieve. And at T equals to T4, this is the condition we are achieving. So from 0 to T4, this was the condition at T equals to 0. From 0 to T4, what diode will feel? From 0 to T4, diode will feel that I am still forward biased only. Because diode says that on N side I am having excess electrons. Sorry, on N side I am having excess holes, and on P side I am having excess electrons. So till going from T equals to 0 to T equals to 4, from T equals to 0 to T equals to T4, till that point diode feels that I am still forward biased. And if diode is feeling that he is forward biased, then what he will do? He will replace himself with short circuit. That means from 0 to T4, what will happen? Diode will say that I am still forward biased, because what diode is feeling? Diode feels like that excess holes are there on N side, excess electrons are there on P side. Until diode feels like that equilibrium is maintained, now he will say that I am not forward biased. But between 0 to T4, diode will say that I am forward biased only. And if diode is forward biased, then what he will do? He will replace himself with short circuit. He will replace himself with short circuit. So diode will be shorted. But what about the battery? Battery is RR and VR. So even though you have applied the reverse bias, but still, because of the excess carrier concentration here, those carrier which were injected from P side to N side and from N side to P side, they are still there. Although they are getting lesser, but still they are excess. Still there are some excess carrier present. So diode will feel that I am still forward biased, and if diode is feeling that I am still forward biased, he will be short circuited only. And since he is short circuited, then this will be your equivalent circuit. This will be my equivalent circuit, where you see the polarity of battery. Polarity of battery is this much, this is your RR. So now how much current would flow? Can you do the circuit analysis? Yes sir. If I am saying that this was my I current, so now my I current is minus VR by RR. Say yes or no? Because the actual current that is flowing is VR by RR in this direction. So now the current that is flowing is minus VR by RR. I can call it IR. This I was calling as IF. Now what I am having? I am having the current as IR, but that current is flowing in the opposite direction. That current is flowing in this direction. Is that understandable to you? Okay, like people actually, they will just read this concept, but they actually don't understand the depth of this concept. What is the depth? What is the actual meaning? That initially diode was shorted for t less than 0, it was shorted, it was driving this much amount of current, VA by RF, no issue. When I change the supply, it has become a reversed bias, but still these excess carriers are not going anywhere. They will take some time. This electric field that has been set up in this position, they will say that holes go back, electrons go back, but they will take some time until they reach the equilibrium condition. Until that time, diode will feel that I am still forward biased only. If I am forward biased, I will be replaced by short circuit. If I am replaced by short circuit, then this kind of condition I am getting. Say yes or no? So if this kind of condition your diode is getting, then this will be your equivalent circuit. So what is the current that is flowing? VR by RR. And that current is minus VR by RR. Why is that so? Because it is in the opposite direction. You are considering that this is your I current. I current has been considered in this direction from P to N. So actual current is flowing from M to V. So that current is minus VR by RR. So here I will write down this current was VF by RF. But now this current we are calling as IR, which is minus VR by RR. Okay, minus VR by RR. So this current is flowing until the time of T4, and this T4 is known as storage time. Okay, this is known as storage time, TS. So if someone asks you what do you mean by storage time? Storage time. So storage time is the time required by the diode to go from excess carrier concentration to equilibrium carrier concentration. Diode was initially forward biased, so he got some excess carrier concentration. Now when you change the biasing, now it needs to go to the reverse bias carrier concentration. It needs to go to reverse bias carrier concentration condition, but what it will do, it will take some time there. The time that it is taking to go from excess carrier concentration to equilibrium carrier concentration, that time is known as storage time. And by example as well, it is clear to you that why T4 is the storage time, because at T4 we are reaching the equilibrium carrier concentration condition. Okay, so here we have reached to the equilibrium carrier concentration condition. Till that point, till Ts, diode will always feel that I was reversed bias only. So till this point, till the storage time, diode is feeling that I was reverse biased only. Now after that, what will happen? After T equals to Ts, after T equals to Ts, now diode will get the feeling that yes, now my carrier concentration is going down. If my carrier concentration is going down, here if my carrier concentration is going down, that means now I need to drive the reverse current, and that reverse current is actually very less. Like here, till this point, diode was feeling that I am forward biased only. Till which point? Till this point, diode was feeling that I am forward biased only. But after this, diode will start feeling that I am reverse biased, and he knows that he needs to drive very low amount of current. In reverse bias, nearly minus I naught current he needs to drive. So what he will do? Now he will start driving very less amount of current. So from here he needs to reach to 0. So he will reach to 0 taking this much of time. Although this time will be very low, like nearly he will reach to 0, or you can say minus I naught. This time is minus I naught. Is that clear? So let me explain it again. From T equals to 0 to T equals to Ts, diode was feeling like that, sir, I am reversed biased. What I am? Sir, I am forward biased. If you are forward biased, then I will be replaced with short circuit. Then the current that I will be driving, that would be VR by RR. Okay, and that current would be flowing from N side to P side. Is that clear to you? Okay. Now, once equilibrium condition has maintained, now the carrier concentration at the edge of depletion, that is going down. So now diode will feel that I am reverse bias, and in reverse bias I need to drive very low amount of current. Actual current is VR by RR, which is very high amount of current. That means I need to drive low amount of current. So the current will start decreasing now, and eventually it will reach to its steady state value, that is minus I naught. So the time that you are taking to reach to the steady state value, that is known as transition time. Is that clear? Basically, this particular time is known as storage time. After the storage time, how much time do you take to reach to this particular value? That is known as transition time. Okay, so let me make it, although this transition time would be very less. In circuit analysis, the whole time we take 0 only. In circuit analysis, what do we say? When it is forward bias, VR by RF, and when it is reverse bias, then it will be 0. In circuit analysis, but actual what is happening, that I am telling. Inside the diode, actually what is happening, that we are telling. Okay, so VF by RF for T less than 0, then for T greater than 0, VR by RR for some time till the storage time, till this particular time. And once the equilibrium has maintained, now diode will say that now I am reverse bias, I need to maintain the reverse bias current. So slowly it will go to its reverse bias current, that is nearly equals to minus I naught only. It could be lesser than minus I naught as well, but nearly it would be equals to minus I naught, which is a very less amount of current. So total time, this is known as reverse recovery time. Okay, that is your storage time plus the transition time. All this theory have been written, you don't need to worry about the theory. Okay, all this theory have been written. So TS is the storage time, TR is the reverse recovery time, TS is the storage time, this TR is the transition time. This is known as transition time. So this is the time which diode is taking to make the transition from forward bias to reverse bias. Like eventually here diode will say that now I have reached the condition of reverse bias. So from equilibrium to reverse bias, whatever the time that diode is taking, that time is known as transition time. And the total time, storage time plus transition time, that is known as reverse recovery time. Okay, so you don't need to worry about these numbers. No one will ask you any question from there. What kind of question can be asked, that we will see in some 5 minutes only. Okay, so yeah, this is the theory. This has been the complete explanation. I hope it is clear to you. Complete theory have been written here. Complete theory have been written. So you can read it on your own. For T less than 0, forward bias VF by RF, T equals to 0, bias is abruptly switched from a forward bias to reverse bias. This kind of condition is there. The diode will not react immediately. It will not block it immediately. because the junction and the neutral region contain some excess stored minority charge. Okay, and during the storage time, what will happen? The diode will still behave like a short circuit only, and a large reverse current would keep on flowing. That current is minus VR by RR. To sweep out the storage charge, this particular current, what this current would do? This current would say that holes will go back, electrons will go back. Right? Here I explained. Holes will go back, electron will go back. Right? And then equilibrium will be achieved. So what is written after that? Once the storage charge is exhausted, that means equilibrium has been achieved here. The diode will enter into transition time. During this time, the reverse current will drop from its peak to the value it is supposed to go. Right? So this has been written. The reverse current will drop from its peak to the steady state reverse level, and that is minus I naught only. The reverse recovery time is given by Ts plus Tt, where TRR, what is TRR? Reverse recovery time. What is Ts? Ts is storage time, and this is your transient time. Okay. Why I have written R here? Transition time is there, no? So this should be written by T. So this is the transition time. This is the transition time. Okay. Only after TRR does the diode reach its stable reverse bias condition, where the current becomes approximately equal to the small reverse leakage current, which is equal to minus I naught. The complete theory is clear. It is one of the most typical topic for a lot of students. They actually don't understand it. They will just remember this diagram, but don't remember the diagram. I hope now everything is clear. That till this point diode is feeling I am forward biased. Here he got the feeling of reverse bias. Okay, and from equilibrium to reverse bias he is going. So this is how he is decreasing the current. Okay, so what kind of question can be asked? Sir, this kind of question can be asked. Whatever that can be asked from this particular topic, that would be this particular question only. Everything I have asked there. What they are asking, I think you will be able to solve on your own. So switch is moved from S1 to S2 at t equals to 0. Storage time is Ts. Comment on V0 and I0 values at t equals to 0 minus, t equals to Ts by 2, t equals to infinity. So what is the circuit at t equals to 0 minus? At t equals to 0 minus. At t equals to 0 minus, this 5 volt, this is not there. For t equals to 0 minus, this particular part is not there. Only this much part is there. What does that mean? The diode will be forward biased. So for t equals to 0 minus, 3 ohm is there, 5 volt battery is there, and this diode is forward biased. And then there is 6 ohm resistance. Right? You need to find out the value of V0 and I0. Very simple network analysis it is. What do you think? What will be your I0? I0 at t equals to 0 minus. That would be voltage divided by 9. Okay, this much ampere. And what will be your V0 at t equals to 0 minus? That would be 5 by 6 into 9, or you can say 5 into 6 divided by 9. Arre bhai, 5 by 9 into 6. That's the answer. Very straightforward, right? So this is coming out to be 2 and 3, 10 by 3. Okay, so 10 by 3 volt. Now at t equals to 0 plus, what will happen? At t equals to 0 plus, this guy is coming into action. S2 is coming into action. 2 ohm, 4 ohm. Diode has become reverse biased? No, diode will still be forward biased. Till what point? Till Ts by 2. So till Ts by 2, diode will still be forward biased only. So that means from 0 to Ts, what will happen? From 0 to storage time, what will happen? This particular thing is changed, but diode will still be short circuited only, because diode is still feeling that I am forward biased only. So what will be the condition? This will be the condition. So this is 4, this is 2. So I need to change the polarity of the battery. 4 volt, 2 ohm, 6 ohm. V0, I0. So I0 at Ts by 2. What that would be? So that would be, it will be actually flowing in opposite direction. No? So that would be, sir, minus 4 divided by 8. Is that clear to you? Why minus 4? Right? I hope it is clear to you. In the opposite direction, the current would flow, no? Actual current that would flow, that would be in this direction. So 0.5 ampere current would flow in the opposite direction. And what will be the value of V0 at Ts by 2? That would be, sir, 6 into 0.5, but minus sign would be there. So answer would be minus 3 volt, right? In the opposite direction. So V0 would be negative. Although this answer I have asked at Ts by 2, but whole answer, all these two answer would be there. Both of the answer would be working for 0 to Ts, right? From 0 plus to Ts, both of the answer would be working. I asked it at Ts by 2. I could have asked it at 3 Ts by 4 as well. It would be same. If I had asked it at Ts by 2, it would be same. Between 0 to Ts, the same condition would be maintained, no? Between 0 to Ts, the same condition would be maintained. That is VR by RR in the opposite direction. The current would be flowing in this direction. That is 4 by 8 minus 0.5 ampere current would be flowing. Multiply with 6, that would be minus 3 volt. Okay. And at t equals to infinity, what will happen? Like after a very long time, reverse bias is achieved, right? Diode will start feeling that now I am reverse biased only. So reverse bias have been achieved. So what will be the current it will be driving? It will be driving the current of minus I naught, right? In this direction, I naught current it would drive, but it is not given. I naught value is not given. So what we need to do? We need to take the ideal case. What ideal case says? Here I said one thing, that in the circuit analysis, if diode is reverse biased, we will take open circuit. So what I will do? I will take open circuit case. Okay. So at t equals to infinity, diode will say that now I am completely reverse biased. What I will do? I will consider myself open circuit now. So diode will consider himself open circuit. So 2 ohm, 4 ohm, and diode will say I am open circuit. Okay, and if it is open circuit, how much current they will drive? 0 ampere. Current is 0 ampere. What will be the value of V0? That would also be 0. So V0 equals to I0 equals to 0. Or I should write down V0 at infinity equals to I0 at infinity equals to 0 ampere. That's it. Okay. So this is the transient on your, this is the concept of transient in PN junction diode. From on to off condition we are going, then how our circuit would behave. So this is how the circuit would behave. Complete theory, and only one kind of question can be asked. From here only they might not give the value of 2 ohm, then directly across the 6 ohm they can ask the question. Like this will be the circuitry. If they ask any question, surely this will be the circuitry. From here to here they will go and they will ask you how your diode will behave according to the given condition. So diode will behave until the storage time. Until the storage time, diode will feel like that I am still forward biased only. Only the current direction would change, but diode will still say that, sir, I am shorted only. If diode is saying that I am shorted only, then do the analysis, and at the infinity, like after the reverse recovery time, after this reverse recovery time, TRR, diode will start feeling like I am finally reverse biased now. So when it start feeling like after T greater than TRR. So at this particular point, diode will start feeling like that I am finally reverse bias. If you are finally reverse bias, then now I can be replaced with the open circuit. So 0 current I will drive, V0 is 0, I0 is 0. Okay. So this topic is completed. Now here I will end our lecture of PN junction under reverse bias. So in this video, we talked about forward bias as well and reverse bias as well. A lot of concepts which were common between reverse bias and forward bias, those concepts we have discussed in this video, right? Now only one small topic is left. Okay, this particular question is left. This particular question we will see in this video only. And then in the next video, we will see this interesting discussion on built-in potential. Okay, very interesting discussion it would be. Like it is normally based on PN junction only. PN junction under equilibrium. It is not related with forward bias, it is not related with reverse bias. But one point I want to tell here. So that discussion we are going to do in the next video. Okay. But as of now, let's discuss this question which was asked in GATE 2022 examination. Okay. So can you try solving, not 2022, it was asked in GATE 2020 because 2022 was my attempt. So it was not asked in 2022. It was asked in GATE 2020 examination. Consider the recombination process via bulk traps in forward biased PN junction. just as they have mentioned recombination. What does that mean? 101% it has to be forward biased. What is the meaning of this bulk trap? So I told you inside the depletion region recombination process would go on. No? I told you the recombination process would be happening inside the depletion region. This is your P side, this is your N side, this is your depletion region. So here inside the depletion region recombination can also take place and generation can also take place, right? In forward bias what will take place? Recombination will take place. What is the meaning of recombination? Electron hole pairs will be recombined. So that recombination and generation is done by trap energy levels. Like there is conduction band, there is valence band. In between there are some trap energy levels are also present. They will generate holes, they can recombine the holes as well. Or similar thing, they can generate electrons, they can recombine the electrons as well. So this is done via trap energy levels. How it is done, you don't need to care about that. You just need to know that generation recombination is the process that would keep on going inside the depletion region via bulk traps. But how they do it, you don't need to care about that. Okay. Even in the Niemann it is not mentioned. Even in the Niemann it is mentioned that trap energy level will be doing the process of recombination and generation. That's it. Even in the NPTEL lectures you would find only this line they would say that there will be trap energy level and generation and recombination process would be taking place because of those trap energy levels. That's it. Okay. So it's not the process that they would be asking, right? Now maximum recombination rate is Umax. Okay. If electron and hole capture cross sections area are equal, then which of the following statement is false? This is what you need to tell. Okay. Now recombination rate, I don't know anything about recombination rate, but I know that how the recombination current takes place. Like why this recombination was into action? Because under the equilibrium this was the condition. And when I applied the forward bias, this was the condition. If both guys were equal, then there was no issue. But because of this thing only, this recombination concept came into action. Otherwise, there would not be any concept of recombination. Because only for these guys, recombination is coming into action. Right? If VA is 0, then recombination rate would be also 0. What I am saying is that if VA is 0, if there is no reverse bias, that means Umax recombination rate that they are saying, that would also be 0. Right? Now, if you let me know, if VA is negative, then recombination rate would be positive or negative? It would be negative, right? Because if VA is negative, that means reverse bias is there. If reverse bias is there, that means reverse bias is there. If reverse bias is there, what does that mean? That means generation is there. So if generation is the opposite process of recombination, generation is the opposite process of recombination. What does that mean? That means that if VA is negative, then Umax would be negative. Umax is the recombination current. This is showing recombination. U is showing recombination. But if VA is negative, then actually generation is happening. So this particular part would become negative. All good? Okay. So let's see which of the following statements are true or false. Let's try doing it. With all parameters unchanged, Umax will decrease if carrier concentration, if intrinsic carrier density is reduced. So only our matter of concern is n into p equals to ni square was the previous condition. Now the condition has become n into p equals to ni square e to the power Va by Vt. Now if ni increases, then this value will increase. This value will also increase drastically, no? What he is asking, that at a particular Va, I was having some recombination current. Now I am not changing this Va, but what I am doing, I am increasing this Ni. Let's just say previously Ni was 10. So previous condition was n into p equals to 100. And then at a particular Va, let's just say e to the power Va by Vt is 10. So now your carrier concentration has become n into p equals to 1000. Now it has become 1000. So depletion width got triggered and he has started generating some recombination current. Now what you have done? You have increased the Ni value. You have maintained Va as it is. That means this 10 would remain as it is, but Ni value has increased. Ni value now has become, let's just say 20. So this part would become 400 and this part would become 400 here. So this part would become 4000. So previously the problem was from 100 to 1000. Now the problem has become from 400 to 4000. That means here the gap was 900. Here the gap is 3600. That means your n into p multiplication is depending on ni square. No, if you are increasing ni, that means ni square will increase, and that is being multiplied with a very high value. Although this e to the power va by bt would be much greater than 10. You know that, right? It would be much greater than 10. That means what is happening? Like your carrier concentration is increasing very drastically. On top level, it might feel like that, sir, here also ni square was there, here also ni square was there. But the problem is, under equilibrium, this ni square was being multiplied with 1. But under forward bias, this ni square is being multiplied with a very higher value than 1. And if this value is very much higher than 1, what does that mean? That means this n into p multiplication will change drastically. This was under equilibrium, but this is under forward biased. So under forward bias, this n into p value will increase drastically if you are increasing ni value. So what does that mean? If ni increases, your recombination also increases. That means first statement is true, that if you are decreasing ni, then recombination will decrease. That's it. So first statement is true. Is that clear to you? Okay, let's leave the statement 2. Let's go to third statement. Umax depends exponentially on the applied bias. Absolutely true. If applied bias increases, then this value will increase and the current will also increase. Like, it is pretty obvious, no? If I increase the bias, if I increase VA, if I am increasing VA, then the carrier concentration from the thermal equilibrium is being disturbed in a very huge amount. If the concentration is being disturbed in a very huge amount, then what will happen? Then recombination current would be more. Recombination current is more, that means recombination rate is more. That's it. So this is pretty obvious. With all other parameters unchanged, Umax increases if thermal velocity of the carrier increases. Thermal velocity. But let's remove here whatever that was required. Now thermal velocity is increasing. What does that mean? How thermal velocity can increase? If thermal velocity has increased, that means surely temperature would have increased. How thermal velocity can increase? Thermal velocity can increase if temperature increases. So if temperature increases, then thermal velocity would have increased. And if temperature increases, I told you temperature and Ni are inseparable brothers. So whatever temperature do, same Ni will do. And if Ni increases, that means recombination increases. And if recombination increases, that means this particular value will increase. That means this statement is also true. A, C, D. So this is what the question paper setter was expecting, that this is how you solve it. They are asking false statement, then this would be false. Umax occurs at the edge of depletion region in the device. That means maximum recombination rate would be occurring at the edge of depletion. So what do you think? Where it would be occurring? Sir, what you have taught? You have taught that, sir, for the whole depletion region, this is what you have taught. For the whole depletion region under forward biased, N into P equals to Ni square e to the power Va by Vt. This is what you have taught, sir. That means recombination should be same in the whole depletion region. If I draw a plot, let's just say this is my minus xp and this is my xn. So inside the whole depletion region, this particular thing will be followed, right? If this particular thing is followed, that means, sir, inside the whole depletion region, the recombination should be same, no? Like this kind of curve you should get. Are you able to understand what I am saying? If I change Va, then electron and hole concentration inside the whole depletion region, whether you are at this point or 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 you are at this point, So inside the depletion region, at all the points, the carrier concentration should be changing by the same amount. And if it is changing by the same amount, that means in the same amount, recombination current should be flowing. And in the same amount, if recombination current is flowing, that means in the same amount there is recombination rate. That means inside the whole depletion region, recombination rate should be uniform. Is that clear? Like if you talk about at this point you know that thermal equilibrium was maintained. Here I was having the value of Nd and here I was having the value of Ni square by Nd. So sir, here thermal equilibrium condition has been maintained. If thermal equilibrium condition has been maintained, that means there is no recombination here. Recombination is 0. And if recombination is 0, that means recombination rate would be 0. So sir, I am pretty sure that here recombination rate would be 0. Same goes for this side as well. Here recombination rate would be 0. But sir, at the edge of depletion, inside the depletion region, here recombination rate would be there. No, for sure there would be recombination rate. What was the carrier concentration plot? Sir, this was the carrier concentration plot. This was the carrier. At this particular point, equilibrium was maintained. At this particular point, equilibrium was maintained. But inside the depletion region, there was an issue. But the formula that we wrote down was this one. And as per this formula, inside the depletion region, the carrier concentration is changing by the same amount. Like if I increase Va, then electron and hole concentration will change by the same amount. So at all the point, recombination rate should be same. So in the examination hall, it might feel like that, sir, this statement is also correct, that at the edge of depletion or at the center of the depletion or here, at all the points, recombination should be same. The rate of recombination should be same. But actual thing is, there was an assumption involved, right? What we said about this Va, this was our PN junction. Okay, so what we said, that whatever the Va we are applying, the whole Va will be dropped across a depletion region, right? And it is true that most of the potential will be dropped across a depletion region only. Let's just say Vf is being dropped across the depletion region, Vf is being dropped. Now, inside the depletion region, how the drop would be maintained? What I mean to say is that, do you remember the Emax graph? Electric field graph. The electric field graph was somewhat like this. So where was the maximum electric field? At the junction, no? So maximum portion would be there at the junction only. So effect of Va will be most at the junction. Inside the depletion region, it would be nearly same, but if I need to pick one point where the effect of Va would be most, that would be at the junction, where P and N are joining. At that point only, maximum effect of Va would be there. Look, sir, it is nearly impossible to get this question correct in the examination. Yes, nearly it is impossible. Like someone who could have done that A, C and D are correct, then he would have clicked on this option B. But again, it is nearly impossible. Till this date, wherever I have seen, what people will do, they will teach something called SRH theory. This is known as Shockley-Reed-Hole recombination theory. They will teach that theory. They will write down 10 formula. From the formula, they will derive something and they will solve this question. Do you really think that you can remember these theories? Like, do you really think that you can remember those formula? They will not derive the formula. They will write down that I actually don't remember the exact formula. Who remembers it? N into P minus Ni square and then NPCT, like different terms would come into action. Then they will act as if they are the best educator in this world, what they have taught, and they will write down these formula, and based on the formula they will solve this question. But do you really think that I will teach in this manner, that you remember the formula and you solve this question? I will write down the formula, then I will say, okay, look, if this increases, then this decreases, if this increases, this decreases, this question is solved. Doesn't make any sense, zero sense. What is my target? My target is to build the intuition that how a student would be approaching in the examination. And if I had been the student who has studied from PrepFusion, then it would click to me for sure in the examination hall that, sir, inside the depletion region, this was the condition. And if this is the condition inside the depletion region, that means till the edge as well, we will follow the same condition. That means whatever that is occurring at the edge of depletion, the same thing would be occurring at the junction as well and here as well. Basically, inside the depletion region, the same recombination rate should be there. This is something that would click to me in the examination hall, because this I derived and I made this graph as well, if you remember, right? And inside the depletion region, we said that this gap is Va. Here the gap became 0, here the gap became 0. That means this was the equilibrium condition. Here equilibrium was maintained. So this was your equilibrium condition. This was your equilibrium condition. The problem was inside the depletion region. So what we said that this much is our depletion region. So inside the depletion region, complete VA is maintained. So whatever that we were discussing, about depletion region. In depletion region, this is how my carrier concentration would be changing. This is what I was saying, right? But if I compare the depletion region itself, then the maximum problem is occurring at the edge of depletion. So maximum recombination rate would be taking place at edge of depletion. And this diagram has been given in Niemann as well. So they have drawn the diagram in this manner. This will be the diagram of recombination. Okay, recombination rate versus X. So till this point it would become nearly 0. Like this point should be xn plus 5 LP, right? Because at xn plus 5 LP you would know that nearly we have reached to the steady state condition. This point should be minus xp minus 5 LL. So here the recombination would become nearly 0. Here the recombination is continuously decreasing. If I talk about at x equals to 0, at the junction, maximum recombination would take place. Again, there was assumption involved that VA is completely dropped equally inside the depletion region, but this is not the case. The maximum problem is happening. The maximum part of VA is being dropped at the junction. That means the recombination would be maximum at the junction. At the edge of depletion, it would be nearly the same, but still somewhat less. Like if I need to compare, like very less difference would be there, but some difference will surely be there. Is that clear to you? It is not clear, but it is what it is. Okay. If you want to read the SRS theory, like 10 formula you study, doesn't make any sense. If they wanted to say that there is SRS theory in your syllabus, they would specifically mention it. And if they would specifically mention it, I would have surely taught it and in a much better manner. Okay. That also I would have taught with respect to intuition only. But this is whole new subject. This is like a whole new subject. It would take at least like 50 hours to understand this particular part. So even the question paper setter did not want you to solve this particular question by this particular theory. Okay. How he wanted you to solve the question in this manner, that at least you are able to say that A, C, D are correct. But if I am a student, what I would see that at least B statement is true. Why? Because I know that at the edge of depletion, there is very high amount of excess charge carriers are there. That means there is very big problem at the edge of depletion. But the actuality is the inside the depletion region, at the junction, the maximum effect of VA is there. And can you remember the graph of carrier concentration as well? This was our graph of carrier concentration, right? On log scale. So let's remove it off. So on log scale, this was our graph. This graph we made, right? And then we said that this is how the graph would go. This is how the graph would go, right? And here this is how the graph would go. So can you see at the junction only you are getting, like this would not be a good logic actually, because everywhere n into p equals to ni square a to the power Va by Vt. Like here the concentration of electrons multiply with the concentration of hole. Here concentration of electron multiply with the concentration of holes. At all the points you would see that n into p equals to ni square a to the power Va by Vt, that would be maintained. But where both of the points are cutting, that would be the point of maximum recombination. So maximum recombination actually occurs at the junction. Okay. But even in the NPTEL lecture you would find out that at a lot of places they have said that recombination would be highest at the edge of depletion, highest at the edge of depletion. Because what we feel, whatever that is happening inside the depletion region, everything is happening the same here as well. But after the junction, everything would start decreasing. So here, the recombination rate would be slightly lesser than whatever that is happening here. So this kind of curve would be there. Slightly here it would be more. So maximum recombination would be taking place at the junction. Okay. Here I have seen different reasoning. Like some people would say that this kind of graph we were getting, like this kind of graph we were getting in equilibrium. So someone would say that, sir, here number of electron and number of holes multiplication is highest. But this is not the reality. In the whole graph, everywhere you go, in the whole condition, n into p equals to ni square, right? And if we make the graph for forward bias, then what kind of graph we make? This kind of graph we make. right? Like this particular part would be constant only. So this kind of graph we make. So you cannot say, sir, here the multiplication is maximum. No, inside the whole depletion region, n into p equals to ni square e to the power va by vt. Inside the whole depletion region. So you cannot say here the multiplication is large. So somewhere I saw this explanation that here the multiplication is large. That's why recombination is maximum at the junction. No. Whatever the multiplication you are getting here, the same multiplication I am getting here as well, and the same multiplication I am getting here as well. Okay, but the problem is the effect of VA is maximum here. So somehow this multiplication actually become larger. Not by this graph. In the graph, if I am making, in the graph I am saying that this multiplication, this multiplication, this multiplication, this multiplication, or the multiplication of these 2 points, all are same. But somehow the effect of VA is maximum at the junction. That's why this particular, at this particular point, maximum recombination would occur. So what does that mean? What you need to remember, you just need to write down one point, or you can make this graph. What you can say is that same graph is given in Niemann as well, that maximum recombination would be taking place at the junction. Okay, so this is your x equals to 0, and you can say that, sir, nearly the same value we will be getting. So this is my x equals to xp, this would be your x equals to xn, this will be your n side, this would be your p side, right? So here I am drawing recombination versus x. Okay, and when I have moved for this much of distance, what is this distance? This distance is xn plus 5 lp, and this distance, this is your minus xp, and so this distance is minus xp plus 5 ln. So when I have reached here, almost the recombination has become 0. Here almost the recombination has become 0, and here the recombination is maximum. Okay, so this is the graph. Again, would be very tough to solve this kind of question in the examination hall. It came for 1 mark only actually. Okay, so you can drop it. This is what I can say. So yeah, here the reverse bias and forward bias both ends. Okay, in the next video we will just see a good discussion about built-in potential, and there our PN junction would end. I hope like at least on Telegram group you would write down that what kind of depth has been covered here, and what kind of things were there. Like you might have felt like, sir, I know PN junction, I know basic semiconductor physics, but now I can see that now you would feel some difference in you, right? No matter from whichever GOD you have studied, a lot of GOD educators are there in this gate field. But I would say one thing about EDC. In EDC, even if I teach EDC for next 30 years, even after 30 years, I can never say confidently that I am 100% sure about EDC, because no one can be 100% sure about EDC. One line I always say, devices are tough. Like those who are very arrogant, like those who feel like that, sir, like we know everything, they actually don't know anything. In their lecture, you would find 10 mistakes. Okay. But those who actually know devices, they would never ever say that we know devices, because no one actually knows devices. What is happening inside the devices, that is very tough to predict, that is very tough to analyze as well. Mathematics is difficult, analysis is difficult, intuition is difficult, everything in the devices is difficult. Okay, so we can never be sure. What we do, we try our best. Okay, so you try your best, I am trying my best. Whatever the knowledge that is necessary at your UG level, whatever the knowledge that is expected from your side, more than enough knowledge would be there in our lectures. Okay, and now we are going to see a very interesting conclusion out of it. This lecture would be also very interesting. It would be hardly 30-minute video. Okay, 20-30-minute video it would be. Okay then, yeah, thank you very much. Happy learning. And if you can share it, if you can talk about this course to your friends or in Telegram group, then it would be better for us, so that it reaches more people. Okay, yeah, thank you very much. Happy learning.